So guys, welcome to the demo session. Good morning, everyone. So myself, Sai Lokesh, working as a senior design verification engineer in S2C Semiconductors, and also working as a trainer in VLSIMINDS. So I'm going to uh, deal the session with this demo session, and also I take the classes on digital electronics, Verilog, system Verilog, and UVM for front-end domain students. Okay. So once again, welcome to the demo session. So let's start the demo session now. So guys, uh, so this demo session will be focused on only front end. That means design verification. So we will explore the other domains as well, but we are not going to in detail in those domains. Okay, I'll just give you an overview about all the domains, but majorly this demo session is focused on design verification domain. Okay, so guys, so let's start the demo session. So in today's session, in today's life, uh, most of us using this electronic systems. So any electronic system you take, okay, so it consisting of 4 layers. Okay, so these 4 layers, any electronic systems you is going to consisting of. So everywhere we are using this electronic system. So without electronics, there is no any application, right? So everywhere you can observe these electronic systems in our mobile phones, in our systems, in our laptops, in our air conditioners, in our home appliances. Okay, so in our automobiles, so everywhere we are using these electronic systems, right? So any electronic system you take, it is going to consisting of 4 layers. Okay, so one is hardware, another one is drivers, another one is operating system, and another one is applications. Okay, so why we are discussing these electronic systems means in the hardware we are going to use some ICs. Okay, that IC is going to manufactured by VLSI. Okay, so very large scale system, very large scale circuits are going to be integrated in the hardware. Okay, so let us go through it step by step. So any electronic system you take, it is going to consisting of these 4 layers: hardwares, drivers, operating systems, and applications. So these are the 4 layers any electronic system is going to consist of. So now let us discuss about all these things in detail. So the first one is hardware. And the next one is drivers. And the next one is operating system. And the next one is end user applications. End user application, right? So guys, so any system you take, so for example, let us take the system as our mobile phone, our regular usage of mobile phone. Okay, so you can see the applications on the display. Okay, so you cannot see what is the operating system that is have, and what are the drivers that are inbuilt on the firmware, and what is the hardware that it is going to consisting of. So these things are invisible to us. What we can see is end user applications. That means for the user, only these applications are visible. Okay, so end user is going to view only this application. So we have many applications in our mobile phone. Okay, so let us consider the electronic system as our mobile phone. Okay, so our mobile phone has a lot of applications. Okay, so if you click on any application, what does it internally do? Okay, so for example, if I click on the application of WhatsApp, what it is internally going to do? Okay, so the electronic system consisting of hardwares, drivers, and operating systems and applications. So if you click on the application, it will internally trigger the operating system. Okay, so the OS, operating system means OS. Okay, and it will internally initiate the driver functionality. And this driver functionality is going to be executed on the hardware. So this is what it is going to do. So hardware consisting of ICs. Okay, integrated circuits, lot of integrated circuits. Okay, so driver means it is going to execute the functionality. Okay, so in order to initiate the execution process, the operating system, in order to execute the functionality of the process, the operating system is there. Okay, so this is what it is going, this is how any system is going to work on. So for example, if I want to open an application, let us consider a WhatsApp. So what I am going to do, so on the display, I'm going to click on the option of WhatsApp. Okay, so once I click on that option, upon I click on that WhatsApp application, it will internally call the operating system. So this operating system will give the information to the driver that this fellow wants to open the WhatsApp. Okay, so the corresponding driver is going to be driven on the corresponding driver is going to be called by the operating system. And what the driver is going to do, so this driver is going to execute that functionality on the hardware. So this is what internally happens when you click on the application. So everything is going to be done in fraction of seconds. Okay, and these things are invisible to us. So if you click on the WhatsApp icon, means you are going to get the chats, and you are going to get the corresponding information related to it. But we never know what is going to happen internally. So this is the internal process it is going to be done. Okay, so that functionality is going to be executed on the hardware. So this ICs, what it is going to do, it is going to execute that functionality. Okay, for example, if I would like to open the chats. Okay, so we have many features in WhatsApp, right? So among those features, which feature has to be accessed? That is going to be the main application, the main execution is done at hardware level, right? So in order to execute these things, so we need drivers. Okay, so this driver is going to execute the functionality on the hardware. Okay, so it is going to have the control on the execution of the functionality. Okay, and which driver has to be called? That is going to be controlled by the operating system. So operating system controls all the drivers on the ICs. Okay, and so when it comes to the drivers part, there could be many drivers. For example, if you take the drivers, so if you take the drivers part, there might be drivers which execute the basic functionalities. So there are some other type of drivers which execute the application specific functionalities. And some other drivers also there. Let us consider some USB driver. Okay, so there are many types of drivers available on the ICs. Okay, so if you click on the WhatsApp, what it is going to do, so it is going to run this type of driver, application specific functionalities driver. That means once you click on the any application, that corresponding functionality has to be executed on the hardware. Okay, and so if you want to access the memory inside your mobile phone, so this corresponding driver, so whichever driver is corresponding to perform the basic functionality, that driver is going to be called. So if you click on any application, this driver is going to be called. And if you connect any other peripheral device to your mobile phone, then USB drivers are going to be called. So there are many drivers are available on your mobile phone. So in order to execute those functionalities, those specific functionalities. Okay, so all these drivers are controlled by the operating system. So it is going to decide which driver has to be called in order to execute the corresponding functionality. Okay, so any electronic system you take, it consisting of these four things. Okay, so the one is hardware. That means the physical chip. Okay, so the main functionality is going to be executed by this hardware. Okay, and in order to execute that functionality in a proper manner, this driver is going to be there. Okay, so this driver is going to control the functionality which is executing on the IC. Okay, so what does this operating system is going to do? So this operating system will control the drivers. That means once you click on any application, so which driver has to be called in order to execute that functionality, that will be controlled by this operating system. And the end user is going to deal with the applications. So once you click on the application, it will internally calls the operating systems. It will initiate the operating system internally initiate the driver functionality, and this driver is going to execute the main functionality on the ICs. Okay, so any electronic system you take, these four functionalities, these four layers are there. Okay, now who is going to develop all these things? So hardware is going to be developed by VLSI engineers. And drivers are going to be developed by firmware engineers. Yes. Did anyone call me? Okay. Guys, at any point of time, if you get any doubts, you can stop me there and you can ask me the questions. Okay. Yeah. So these drivers are going to be developed by firmware engineers or embedded engineers. And operating system is going to be developed by software engineers. And the end user applications are also developed by software engineers. Okay, so each and every layer is going to be developed by the respective engineers. Okay, so the operating system and applications and user applications are going to be developed by software engineers. So we are not going to deal about these things. And drivers are also developed by firmware engineers or embedded engineers. Okay, so we are not going to concentrate on these things as well. So the main hardware, that means the physical implementation of the functionality. Okay, so that we are going to discuss about. So VLSI engineers are going to develop the physical implementation of the functionality. That means the ICs are going to be developed by this VLSI engineers. Okay, guys. So applications are developed by software engineers, right? So they are going to use some languages, programming languages. Either it can be C++ or Java or some Python, some other languages they are going to use to develop the applications, as well as they are going to use some other programming languages to develop the operating systems. Now, when it comes to drivers, okay, so firmware engineers are embedded engineers. They are going to use System C. Okay, so System C to develop these drivers, because this driver is going to be act as a communication barrier between this hardware and this operating system. So this operating system cannot understand the hardware language, and this hardware and this IC cannot understand the instructions which are given by this operating system. So driver will be acting as a communication barrier between this hardware and this operating system. Okay, so it needs to understand both the things. I mean,
So the system C is a language or a library?
sorry?
What is the system C? Is a language or what?
System C is a language, so it is not like a regular C language, so it has some other advancements. So as I'm telling you, right, so it has to understand both the things. It has to understand the software language, because the operating system is going to given the instructions which are in the form of software things. Okay, but the hardware is going to be developed by some hardware description languages. Okay, they are mainly focused on the functionality related. Okay, so they will be mainly focused on what type of functionality it needs to execute, and what type of operation it needs to perform. So those things are there in hardware. But software, software languages are different. So we are going to look into it, the difference between the hardware description languages and software languages. Okay, so System C is a language. Okay, so it is not a library, it is a language, but it is just not like our regular C language. So it has some advancements. Okay, it needs to understand both the things, both the software things as well as hardware things. Okay, so that is why they have developed one unique language, that is System C, which can understand both the things. Okay, so it is a language. Okay, it is not a library, it is a language.
Okay, sir. I thought C++ System C is a library from C++.
No, 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 no. It is a different one. Okay. Yeah.
Okay.
So firmware and embedded engineers are going to use System C to develop the drivers because it needs to execute the functionality on the physical chip. That means on the hardware, it needs to execute the functionality. Okay, so we don't focus on these things, these three things. We will mainly focus on the hardware. That means how the chip has to behave. Okay, so what considerations you need to take while development of the chip. Okay, so those things we are going to deal with. So VLSI engineers are going to deal with the hardware part. We are not going to deal with the drivers and operating systems or the applications. So in the electronic system, any electronic system you take, our focus is mainly on the hardware part. So we are not going to deal with all these things. Okay, our main intention is to if it is a design part, we have to develop the hardware part. Okay, so if it is a verification part, you need to check the hardware. Okay, so if it is a some other domain, so anything you take, any domain of VLSI you take, we mainly focus on the hardware part. So this is the introduction about the VLSI engineer's job role. Okay, so we mainly focus on the hardware of the chip. We are not going to deal with the rest of the things. Right, guys? So, just 1 minute. So we are going to deal with the hardware. So which is going to be developed by VLSI engineers. Okay, so now, what is this VLSI? So the acronym stands for Very Large Scale Integration. Very large scale integration means, large scale means we are going to deal with the millions and billions of the transistors. Very large scale means we are not going to deal with the tens of transistors or hundreds of transistors. We are going to deal with the millions and billions of transistors. Why we are dealing with millions and billions of transistors? Because in order to get some functionality, we have to integrate those many transistors together. Okay, so in order to get some required functionality, for example, I would like to get some functionality as I have to connect to the GPS. Okay, I have to connect to the camera. I have to connect it to the some other peripheral device. So in order to get that type of functionality, what you need to do, you have to integrate lot of transistors onto a single chip. That is why we call it as a very large scale integration. We have to integrate number of transistors in order to get some specific functionality. Okay, integration means nothing but combining. Okay, so large scale means we are going to deal with the number of transistors. Very large scale means in terms of billions and millions. So it is the process of integrating millions and billions of transistors onto a single chip in order to get a required functionality. Right. So what is the purpose of using this VLSI? That means why do we need to integrate those many transistors? Because in order to get some functionality in a compact size and high speed, that means so we have to deal with the high speeds, right? Because we don't want to experience any delay while execution. Okay, so we need everything in fraction of seconds. We need every job to be done in fraction of seconds. Okay, so once you give the inputs to any system, you have to get the output instantly. Okay, so we should not face any delay. That means high speed performance we require. So in order to get that high speed, we need to integrate many transistors. Okay, and so there are some optimization techniques are there which are used to compact the size of the IC. That means if you take an IC, for example, in 1990s and 1980s, we used to observe the systems which are bulk in it. I mean, which has a very big size, right? But in nowadays, we are not seeing any such type of computers, right? So any laptop you take which are lesser in size, and which has more flexibilities to the user and lesser in weight. Okay, so the ICs are very, very compact in nature. So if you have been observing from 90s to till today, the size of the chip has been decreasing day by day, right? So initially, they used to work with the computers which are very bigger in size. Okay, that means you can imagine the size of the chip that they have used. Okay, but nowadays we are using a chip which is very, very compact in size, right? So in order to get all these benefits, we have to use VLSI and low power electronic systems, and the power consumption is also being reduced. Okay, and it is the purpose of using VLSI is to reduce the size and cost and power consumption, and reduce the power consumption of the circuits as well. So if you take the evolution of the IC technology, initially they used to work with the small scale integrated circuits. Small scale means hundreds and thousands of transistors. After that, they went to medium scale integrated circuits. Medium scale integrated circuits means 10,000 transistors and 1 lakh. After that, even then also they were unable to get the required functionalities. That means the speed that they need to acquire, they were unable to acquire that speed. That is why they went for large scale integrated circuits. Large scales deals with lakhs of transistors. But even then also they were not satisfied. Okay, that is why they went to VLSI. That means very large scale integrated circuits. So in order to get the required functionality, that means it can be that functionality might be related to with respect to speed, or with respect to power, or with respect to frequency, or with respect to size, anything you take. But in order to meet that functionality, they went to this VLSI. That means very large scale integrated circuits. So the integration level has been increased with the advancements in the semiconductor technology. So they worked with 14 nanometers, they worked with 6 nanometers, they worked with 2 nanometers, they worked with, the market now is going with the 3 nanometer technology. So, and still they are working on the 2 nanometer technology. Okay.
So
So
why that number is scaling like 8 to like that? Why not 7?
okay. You're asking about the size of the chip, right?
Yes, sir. Is scaling about scaling.
Actually, we cannot fix any. I mean, it depends on the optimization techniques, Harshit. So if you take the technology evaluation, so
Yes, sir.
initially, at the starting of the at the starting of this array, they worked with 14 nanometers. After that, they went with 9 nanometers. So now your question is, after working with 14 nanometers, why didn't they work with 13 nanometers? Why
Yes,
didn't
sir.
they work with
Exactly.
12
Exactly.
nanometers? Why didn't they
Yes,
work with
sir.
10 nanometers? Why they directly went to 9 nanometers? That's what your question,
Exactly.
right?
Yes, sir.
Yeah, actually, it depends on actually, we need to follow some optimization techniques, Harshit.
Okay.
Okay. So this optimization techniques, uh, we will have in the domain of placement and routing.
So why not while designing the standard cell?
While designing,
Standard cells.
uh, I didn't get your question. Come again. Why don't we use standard cells? I mean,
Sir,
with respect.
placement and routing will comes under physical design flow now, sir.
Oh, okay. So, see, Harshit, placement and routing means they are going to follow some optimization techniques. So, how they need to place the standard cells?
Sir, in
Okay.
the standard cell only we have this technology nodes like 14.9, like that. In that I'm asking.
Yeah. So in the standard cells only, they are working with this sizes only, but they have to follow some techniques, right? So how I mean, so how, in which manner you have to place all the standard cells in order to get the best out of it. Okay,
Yes.
so based
Yes.
on that, they went with 14 nanometers and they went with 9 nanometers. So even at the starting, they might be tried with 10 nanometers as well. They might be tried with 11 nanometers as well. But once they went with the 10 nanometers and 11 nanometers, they might not get the required functionality. So the reducing of the size, the reducing the size of the chip is not only the thing, right? So by
Yeah.
reducing the size, they have to meet the other
Functionality.
facts also. That means the power has to be low, and the functionality should not be compromised, and the frequency should not be compromised. So while reducing
Yes.
the chip, they have to meet the all other aspects as well. Okay, so they have to
Okay.
balance both the things. They have to reduce the size, and at the same time they have to meet the power requirement, and at the same time they have to meet the frequency requirement, and at the same time they have to meet the required functionality. So by taking all the things into consideration, they went for these things.
Okay.
Okay.
So one more doubt.
Huh.
Sir, in a single chip, we can use multiple technology nodes or a single technology node
Uh,
transistor.
Actually, as per my knowledge, they have to go with only a single type of technology. As per
Sir,
my
if
knowledge.
we are working with low power technology, we need to move on with the multi threshold gates.
Hmm.
In multi threshold gates, in the 180 nanometer, we don't available that multi threshold gate. It was available only for 14 nanometer and all.
Hmm.
Uh, to reduce the data path delay or other delays, we need to use multi threshold. It will be useful or not? I'm asking.
Uh, I mean, so would you like to go with the different technologies in a single standard cell?
Yeah, that's what I'm asking. In multi technology nodes, we are using or a single technology node. If you
Actually,
take an example of Qualcomm chips,
Qualcomm
they are- they
chips.
are men- they are mentioning we are invented 2 nanometer chips and all. It
Hmm.
the all the transistor which are there in the chip will be only a 2 nanometer or some higher
Actually,
grades. Oh,
no. I think, as per my knowledge, it is not multi technologies are going to be involved in a single chip. So Qualcomm is going to produce the chips. That means they might go with 2 nanometers and they might be go with 3 nanometers. But this 2 nanometer chip will be used for one purpose, and this 3 nanometer chip will be used for other purpose. So as per my knowledge, they are not going to mix multiple things into a single chip.
why? Because if we scale down the technology nodes,
Uh,
the performance of a circuit will be increasing, but the subthreshold leakage will go on increasing, now, sir.
yeah, that's what I'm talking about.
Okay.
So they have to meet all the standards, right? So actually, I don't have much knowledge in the placement of the standard cells, but as per my knowledge, as with my experience, I'm telling you that. So there is no possibility to include multiple things onto a single one,
Okay,
because
sir.
2 nanometer technology will work with one type of power, and 3 nanometer technology will work with another type of power. That means
It means in the VDD
in terms of
voltage required for
Ah,
the transistor.
yeah. So voltage and power dissipation, all the things we need to take into consideration.
We
Okay,
can use the level shifter in between them, no, sir.
level shifter, right? That is what
Yeah.
I'm telling you about. So,
Ah,
for example, if you are mixing 2 nanometer cells and 3 nanometer cells onto the same chip, that means, for example, in this manner,
yes, sir.
this is going to work with 2 nanometer, and this is going to work with 3 nanometer. So let us consider this is going to work with 0.25 volts, and this is going to work with 0.31 volts. So let us consider in this manner. That means what you need to do. So for all this chip, if you are giving a supply of 1 voltage, then what you need to do, you have to take two level shifters in order
Yes,
to bring 1 voltage level to 0.25 voltage and 1 voltage level to 0.35 volts.
exactly.
Okay, so two level shifters you have to use. That means you are making the
Increasing the hardware
system.
size.
So you are increasing the hardware size, right?
Yeah.
And So we are just talking about only two cells here, right? For two cells, we need two level shifters. But
Yes, sir.
when it comes to a higher large scale, that means how many level shifters you have to use, you can imagine, right? So generally, we are
Exactly.
going to use the cells in a bulk in nature, right? That means unnecessarily you are increasing the size of the chip by many times,
Yes, sir.
right? Right, Harshit?
Exactly, sir. Correct.
So, for example, instead of going in this manner, if you make use of only 0.25 volts, I mean, only with one technology, that means two level shifters you don't need to use. Only one level shifter is enough to supply the power to this chip, right? To this cell, right?
Yes, sir.
So we can decrease the size of the chip, right? So
Okay.
as per my knowledge, so only one technology is going to be used in cells. Okay, but
Okay, sir.
it also depends on the requirement as well. For example, there may be some areas you may need to include multiple technologies on the same chip, but it is very rare. So
Okay.
not everywhere we are going to use it, but if there is any particular necessity, then we can go with these things.
Okay. It is possible.
I mean, they have
Okay.
to go with some things. Okay, they have to go. It is possible, but they have to
Okay.
consider the other things as well. They should not compromise on the performance. That is the major
Is
thing.
that is that chips available now?
Uh,
With
I mean, maybe available,
oh,
but I
okay.
don't know about it. I'm not aware
Okay.
of those things. But
Okay, sir.
as per my, I mean, I'm thinking that there might be.
Okay,
Okay,
sir. Okay.
because
Thank you.
everywhere we are not, I mean, for example, if we take our regular applications, mobile phone or laptop, so we are not going to do with the complex things.
Yeah.
Okay, so we
Yeah.
use all these things for the basic functionalities, right?
Yeah.
But
Yes, sir.
when it comes to an defense sector, or when it comes to a
Exactly.
satellite,
The size is not a parameter for them.
yeah, so the size is not a big issue for them. Okay, but they have
Yes,
to
sir.
meet their requirement. Okay, so
Exactly.
one
Yes,
thing has to do multiple functionalities, right? So then
exactly.
there is a necessity to use all these technologies. Okay,
Thank you, sir.
so we have to go with the optimizations, Arshit. That means what is our requirement? Whether are we going with the basic things, or are we going with the advancement things,
Okay, sir.
right? Yeah. Where were we? Yeah. So now, so where are you using this application? I mean, where are we using this VLSS? That means anything you take, whatever the application you take, everywhere we are using this VLSI. So we are dealing with the microprocessors, we are dealing with the mobile phones, we are dealing with the laptops. So these are the basic things which we are using in our daily life. Okay, so in smart TVs, embedded systems, automotive, electronics, and the trending technologies like artificial intelligence and IoT devices. This VLSI is the fundamental thing. Okay, so everywhere we are using this ICs, which is based on VLSI technology. Okay, so that is why the market is now going with the VLSI technologies. Okay, so there are huge opportunities for VLSI. Okay, because everywhere we are using. So can you imagine your regular life without using your mobile phone? Can you imagine your life without using any laptop, right? So in present days, we cannot imagine our life without all these things. Okay, so everywhere we are using these applications in our home appliances as well, in our washing machines, in our smart TVs, in our air conditioners. Everywhere we are using this ICs. Okay, so that is why most of the students are interested to take their career in VLSI because of the huge applications. So from basic applications to advanced applications. Okay, so now how are we going to design this VLSI chips? Okay, so there are two styles to design the hardware of VLSI. So what are those two styles? One is ASIC and another one is FPGA. So ASIC means application specific integrated circuits. FPGA means field programmable gate arrays. Okay, so the VLSI hardware, I told you, right? So VLSI engineers are going to work on the hardware of the chip. Okay, so this hardware can be designed in two ways. One is ASIC and another one is FPGA. ASIC means application specific integrated circuits. FPGA means field programmable gate arrays. Now, what is the difference in these two styles? So the name itself indicating that application specific. Okay, and FPGA means field programmable gate array. Field programmable. That means application specific integrated circuits. Okay, so in these ASICs, the IC is going to be manufactured when there is a requirement. Okay, so if any client comes to a company, that means I need this type of IC to be manufactured. Okay, so he has some requirements. Okay, so the IC has to support those functionalities. IC has to consume some power. IC has to work with some frequencies. So he is going to come up with some requirements. So only when client comes to a company with his specifications, then only the integrated circuit is going to be manufactured. And this IC is meant for only that application. Okay, so it cannot be used for the other applications. Now, FPGA. FPGA means field programmable gate arrays. Field programmable gate arrays. That means what it is going to do. So you can correlate this one with the thing that you already used in your EDC labs. So in our BTech in third semester or fourth semesters, we might have used these breadboards, right? So in order to make the connections, we used breadboards, right? In the same way, FPGA boards are already available. For example, if you take any breadboard, okay, so breadboard is available in this manner. So in the breadboard, what we are going to have, we are going to have some connections. Okay, in this manner, we are going to have some connections. So this breadboard is already available. So depending on the requirement, what you need to do, you have to make the connections. For example, you have to make a connection to get some required functionality. And you have to make another type of connection to get another type of functionality. And another type of connection to another type of functionality. Okay, so this functionality is different, and this functionality is different, and this functionality is different. So the breadboard is already available. So depending on the necessity, what you have to do, you have to make the connections. You have to utilize these connection points. Okay, so in the same way, in FPGA, some FPGA board in FPGA hardware coding, hardware styling. So some FPGA boards are already available. Some connections are already made. So what you need to do, so depending on your requirement, you have to program everything. Okay, for example, I need to get some one type of functionality, then you have to make the connections in certain way. Okay, so from the available board, you have to program on it. Okay, so you have to design the things based on your requirement. Okay, already breadboard is available, so you have to make the things. That means you have to customize the things. Okay, or you have to configure the things as per your requirement. So when you have a necessity, then you are going to configure it. Okay, if you don't have any necessity, the breadboard will be available as it is, right? But in application specific integrated circuits, no boards are available readily. Okay, so you have to develop everything from the scratch. Okay, so whenever there is necessity to manufacture the chip, then only you have to develop the IC. Otherwise, there is no need to develop the IC. So whenever client comes to you with a specific requirement, then you are going to start developing it from the scratch. But in FPGA, you don't need to develop it from the scratch. By default, already breadboard is available. Okay, some FPGA boards are available. Some they are going to program something inside this FPGA. So based on your function necessity and based on the functionality that you want to get it from this board, you have to configure the things. That is the difference between ASIC and FPGA. Okay, so now let us understand the difference between this ASIC and FPGA through some examples. Okay, so when it comes to an application specific integrated circuits, so I told you one thing, that so this IC is meant for only this application. For example, what are the home applications do we have in our regular life? So in our regular life we do work with mobile phones, we do work with laptops, and some ICs we use in smart TVs, and some ICs we use in air conditioners, and some ICs we use in washing machines, and some ICs we use in our automobiles. Okay, so what is the purpose of using mobile? So we do use many applications in our mobile phone. Okay, so laptop means it can be related to anything. For example, I'm using it for business purpose. Okay, and smart TV, we used to watch some songs or something else. Okay, and air conditioner, what is the purpose of using air conditioner? To control the temperature. Okay, and washing machine means what is the purpose of using IC in washing machine? So washing machines means it needs to control the speed of the motor. And when it comes to automobiles, that chip has to deal with many things. For example, it needs to be connected with the gear system in order to control the speed, and it needs to connect with the GPS, and it needs to connect with the braking system. Okay, and some it needs to connect with the some other things as well. So automobiles means mainly we use it for traveling, right? So it needs to connect with the gear system, it needs to connect, it has to control, it has to be enabled with the GPS, and it has to control the braking system. All these things this IC has to deal with, right? So some ICs we are using it for mobile phone, and some ICs we are using it for laptops, and in this way we are going to use ICs everywhere, right? So these are application specific. That means whatever the IC that you have developed for mobile phone, it is meant for only mobile phone. It cannot deal with the other things. For example, so the IC I have developed it for mobile phone. Can I use this IC to control the speed of the motor in washing machine? No, it cannot do. Okay, so IC in the washing machine, what is the purpose of IC that we are using in washing machine? It has to control the speed of the motor. Sometimes the speed of the motor has to be increased. Sometimes the speed of the motor have to be decreased. And sometimes it has to rotate in leftward direction. Sometimes it has to rotate in rightward direction. Okay, so those things are going to be handled by this IC which we are using in washing machine, right? But all these things can be done by this mobile IC? No. So what is this IC is going to do? So it is going to deal with the applications. Okay, so the main focus of mobile IC is it has to open the applications. It has it has to work with some frequency. Okay, and it has to deal with some other applications. So mainly we are using this ICs for mobile application. It is not going to deal with the speed of the motor. And laptops, and that means it is going to deal with some business purpose. That means it is going to run some specific specific softwares. Okay, so it is going to execute some programs. Okay, so all these things are going to be handled by this laptop ICs. Can I use this laptop IC in the air conditioner? No, because air conditioner IC is to control the temperature. Sometimes depending on the user's requirement, it has to either increase the temperature or decrease the temperature. So it has to configure the compressor. Okay, so that functionality will be there for this IC which we are using in the air conditioner. So the IC are application specific in all these applications. Okay, so one IC cannot do the job of other IC. So that is why we call it as application specific integrated circuit. This IC is meant for only this application. We cannot use this IC for other application. So even you try to make use of this IC in other application, it won't work. Okay, so that is application specific. The next one is FPGA. Field Programmable Gate Array. That means we have already seen the introduction part of this FPGA. So what is that? So the basic functionality is already there in the FPGA boards. That means in all the FPGA boards, basic functionality is already designed. Okay, so what you need to do, so along with the basic functionality, you have to implement some other advanced functionalities. Okay, so what is that other advanced functionalities? So let us consider an example. Okay, so if you take the rocket system. Okay, so what is the main purpose, or what is the main basic functionality of the rocket system? The rocket's main basic functionality it has to take the satellite from ground to Earth orbit. Okay, so this is the basic application of any rocket system. So it has to take the satellite from ground to Earth orbit. Okay, so after entering into Earth orbit, what is the other things it needs to do? So some satellites functionalities. So some satellites are meant for weather forecast. Okay, so some satellites are meant for communication. Okay, some other satellites are meant for some research application. Okay, some other satellites are meant for to take the pictures and to analyze the soil behavior of other planets, right? So planet information. Okay, so after entering into Earth's orbit, the satellite usage will be different. But what is the basic functionality of any rocket system? It has to take the satellite from ground to Earth's orbit. So any rocket system you take, this is the basic functionality. That means you can use this FPGA boards to execute this basic functionality. So any rocket system you take, it has to take the satellite from ground to Earth's orbit. After entering into Earth's orbit, what is the advanced functionalities? So some satellites are used for weather forecasting. That means it is going to execute this functionality only. It is not going to deal with the remaining functionalities. And some satellites will be meant for communication purpose. And some satellites are meant for research purpose. In that way. Okay, so for all these satellites, basic functionality is common. What is that basic functionalities? They have to be bring from ground to Earth's orbit. That is the basic functionality. Once they enter into Earth's orbit, their functionalities will be different. Okay, so for all these things, you can make use of FPGA. That means some board will be there. In that board, FPGA board, some basic functionalities are already defined. So along with the basic things, what are the other advancements you want to do it? Okay, what is the other advanced functionalities you want to get out from that FPGA? Okay, so if you use it or don't use it, already the breadboard is available. So if you want to get some functionality along with the basic functionalities, if you want to get from other advanced functionality along with the basic functionalities, you can configure the board as per your requirement. Otherwise, you are going to get the basic functionality of the FPGA. Okay, so if there is any requirement, then you can configure it. Otherwise, no need. But by default, some FPGA boards are available. So by default, some boards will be manufactured. Okay, but in case of application specific, whenever any requirement is there, at that point of time only IC is going to be manufactured. Otherwise, IC is not going to be manufactured. That is the difference between ASIC design type and FPGA design type. So in ASIC design type, the IC is going to be manufactured when there is a requirement. Okay, but in FPGA type, some breadboards, some FPGA boards are already available. So when there is a requirement to execute some other functionality along with the basic functionality, then you can configure it. Otherwise, you can go with the basic functionalities of the FPGA boards. Okay, so you need to implement some optimization techniques and you need to implement some prototyping. Okay, all these things in order to get some advanced functionality. Okay, that is the difference between ASIC design type and FPGA design type. So in practical, most of the times we are going with ASIC types. Okay, that is why we are going to deal with this ASIC flow. So if you open the SoC architecture, SoC means system on chip. That means many modules are going to be integrated onto this chip. Okay, so this is the SoC, system on chip. That means many systems are going to be integrated onto a single chip. So if you open the hardware on your system or your mobile phone, the system is going to be look like in this manner. Okay, so in that system, one CPU subsystem is there. So this is going to control every application on this system. So the mainly ARM processors are going to use to control the all systems. A series are there, R series are there, and M series are there. So all the series are going to control all the systems on the SoC. And along with these things, you can find out some design specific subsystems are there. That means what type of design you would like to work with. Okay, so for mobile phone, some type of designs are going to be used, and for laptop, some other purpose uh, designs are going to be used. And even in the laptops also, what is your priority? So would you like to go with the business purpose? One type of design will be adopted. So if you are going with some gaming purpose, then other type of systems are going to be adopted. So depending on your requirement, design specific subsystems will be available. And as per your requirement and as per your necessity, some GPUs are going to be used. GPU means graphical process unit. Okay, so this is the GPU is going to control the resolution of your system. Okay, and what type of quality of the picture you would like to see on the monitor. Okay, and what type of pixel format you would like to use. So everything is going to be controlled by this GPU, graphical processor unit. Okay, so all the colors that we are looking at on our monitor because of this GPU. Okay, so it is going to control the screen resolution and the pixel format and the quality of the picture. So everything is going to be controlled by this GPU. And the
So what
next
do you
one
mean by
is,
subsystem?
sorry,
What do you mean by subsystem?
subsystem. Okay. So subsystem means generally, for example, if you take your mobile phone, okay, so camera is one IP, intellectual property. Okay, and Bluetooth is another IP, intellectual property. And memory is another thing. And GPS is another thing. So as of now, these are individual things. Okay, so camera is going to work independently. Bluetooth is going to work independently. GPS is going to work independently. So now, when you integrate all of these things, we call that one as a subsystem. That means
Okay.
inside the subsystem, you are going to integrate all these things. Okay.
So by all these hardwares are controlled by drivers.
All hardwares,
Are controlled by drivers, as you
drivers.
said before.
Yeah, exactly. So if you connect camera with the Bluetooth and these two things with the memory, when you integrate all of them, integrating means making connection in between them. So this whole thing, we call it as subsystem.
Okay.
Okay, so along with all the modules, if you include the processor, that means this one, CPU, that we call it as SoC, system on chip. Okay, so subsystem means we are integrating all the individual modules. So along with the modules, if you introduce processor into them, we call it as a system on chip. Okay,
Okay,
and
sir.
some application subsystems are also there. These are application specific. That means if you need any specific application into your system, then they are going to introduce it. Otherwise, there will be no need. Okay, so you can find out these type of application subsystems mostly in automobiles. Okay, so if you take the example as an automobile, so the user's requirement will be different from individual to individual, right? So some might need a radio system in their automobile and some might not need it. Okay, some needed some others requirements. Okay, so based on his requirement, they are going to introduce these application subsystems. Okay, so along with these things, we also have memories. Okay, so cache memory, main memory, RAM, ROM, all these things are going to be there in memory subsystem. Okay, so and with these things, we also have some protocols as well. So protocols means, for example, to my laptop, if I connect pen drive, so pen drive is a peripheral device. Peripheral means some external device. So that is not the part of the that is not part of my chip. That is not part of my system. Some external device has been connected to my system. Now, how the communication has to happen between
By using AMA protocol,
sorry
we can use APB.
Harshit, AMBA protocols are different. Those are on-chip protocols. Okay, so there are two types of protocols. Okay,
Sir, what
so
about APB? APB.
APB is an AMBA protocol.
Yeah,
Okay,
it's for peripheral, right?
it is not a peripheral. The name, the acronym is Advanced Peripheral Bus, but
Okay.
the context is different, Harshit.
Okay, okay, sir.
Okay, so we will
Okay.
discuss about those protocols after some couple of minutes. So what type of protocols are there and how the communication is going to happen. All these things we will discuss in a couple of minutes. Okay,
Okay, sir.
so now when any external device is connected to it, how the communication has to happen between this chip and that peripheral device, that is going to be controlled by these protocols. So guys, whenever you come across with this keyword protocol means, don't think too much about it. Protocol means some set of rules you need to follow. So when it comes to our domain, VLSI domain, so we deal with the data transfer, right? So the data transfer can be within the chip, within the modules, or the data transfer can be from the system to outside device. Okay, so these protocols are specified to deal with how the data communication has to happen between two modules. That's it. So protocol means in general usage, how we use that keyword protocol means some set of rules you need to follow. So for what purpose you need to follow those rules when it comes to VLSI domains for the data transfer, how the data communication should be done between two modules. Okay, so protocol means it is going to list out some rules you need to follow while transferring the data from one component to other component. In VLSI, whenever you come across this keyword protocol, you have to understand this one, right? So all these protocols will be there. So when you connect any USB device, how the communication has to happen. When you connect any Ethernet cable to your system, how the data communication has to happen. So all these things are there in this section. Okay, so along with this, we have Wi-Fi enabled and GSM enabled, LTE enabled. So depending on the technology, you are going to use this wireless subsystems. Okay, and along with these things, some other protocols are also there. That means MIPI protocol. MIPI protocol means it is meant for camera serial communication. That means if you are opening a camera, it has to capture some picture. Okay, so after capturing the picture, the data has to be stored in the memory. But so once you click on the picture, it is going to be stored in a pixel format, right? But if you have to convert that into PDF format or JPEG format or some other format, So what you need to do, so you have to convert the data from one form to other form. So how everything is going to be taken care, that is going to be controlled by this meeting. Okay, so once you click on anything, it has to be stored in the memory. Okay, so within the traveling of after capturing that information, it has to be stored in the memory, right? So in the traveling of that information, what set of rules you need to follow. So all the things are going to be present in this system. Okay, so remember one thing, guys, subsystem means nothing but when you integrate individual modules, that system we call it as a subsystem. Okay, but along with the subsystem, if you introduce processor into it, we call that one as SoC, system on chip. Okay, so in system on chip, processor will be there. In subsystems, in most of the subsystems, in many cases, processor will not be there. Subsystem means nothing but you are integrating some modules together. Okay, so the next one is ASIC flow. So as I told you earlier, we mostly go with the ASICs. That means application specific ICs. Okay, that IC is meant for only that application. It cannot be used for other application. So while designing the IC, what are the things that you need to follow? That described by ASIC flow. Okay, so in this ASIC flows, various domains are available. So in all those domains, job roles are available. Okay, so you can choose your career as per your interest. Okay, so my suggestion is that, so for all the VLSI domains, equal opportunities are there. Okay, so choose your career as per your interest. Okay, that is my suggestion. So if you are good at coding, find out the domain which is on the coding. If you are not good at coding, if you are good at optimization, okay, then find out the domain related to that one. Okay, so never think of the salary and never think which one is easier and which one is not easy. So if you find out the domain which is very related to your passion, then you would find the job very easy, right? So my suggestion is to, based on your interest, choose your career. Okay, that is what my suggestion. So we will discuss, so if you are good at what type of domains you can go with, if you are good at optimization techniques, what type of domain you can go with. Okay, we will discuss that one. So now let us consider in ASIC flow, that means while designing any specification, any application specific integrated circuits, what is the flow that you need to follow? Okay, so guys, this is the flow. That means first user will come up with some specification, chip specification. What is meant by chip specification? Specification means nothing but a document. Okay, so let us discuss this thing, ASIC flow. So ASIC flow consisting of first, user will come up with some specification. Okay, so what is meant by a specification? Specification is nothing but it is a document which consists of user's requirement. That's it. So user will come up with the specification. That means he has some requirements, right? So what could be that requirements? So it can be related to the frequency that chip has to work with. Okay, so it can be 2 gigahertz or 2.5 gigahertz or something else. Okay, so with what frequency the chip has to work with, and this other details might be included with some power consumption. That means this much of power the IC should consume. Okay, and the power consumption should not be greater than within certain range. Okay, so it should not cross that limit in that manner. And some functionalities.
Input and output pins.
Sorry.
Input and output pins required.
Sorry, Harshit, I did not get you. Can you please come again?
Is the pins required? Inputs and outputs pins available. So
Yeah, so that is also one of the specification. So IO pins or peripherals, it can be. IO pins or peripherals, peripheral points. And some other things as well. That means what are the clocks that modules has to
area,
work.
area, so
Yeah, area that I'm going to write it. So clock signals requirement. And the size of the chip. So this much size of the chip that he has read. So it can be anything. So the specification means it is nothing but a requirement of the user. That's it. So what type of things the chip supposed to meet. Okay, so with what frequency it has to work with, how much power it should consume, and what are the functionalities. Functionality means that can be related to an intellectual thing, or it can be related to a logical operation, or it can be related to a storage purpose, anything. Okay, so functionality means it has to perform something. Okay, and what are the IO pins? That means input output pins does it need to support. Okay, and what are the clock requirements? That means how many modules are there inside the chip, and each module is going to consume how much amount of power, and based on that how many clock cycles do we need to use. And each module, what type of which module is going to consisting of how many clock cycles in order to transfer the thing, or in order to perform anything, in order to perform the specific functionality, how many clock cycles does it need. Okay, so based on the clock requirement. And what is the size of the chip? That means how much size the chip has to consume on the how much what is the size of the chip that is need to be supposed to. Okay, so all these requirements are comes into the category of specification. Specification means the user is going to list out his requirements in one document. That document we call it as a specification. So once he come up with the specification, the next thing is, after user comes with specification, he will give that specification to the architect. So one job role is there, that is architect. That means who is going to design the entire project flow. Architect is going to design the entire project flow. Project flow means so he has got the specification from the user, right? In order to get that job done, how many design engineers are required? How many verification engineers are required? And what should be the size of GLS team? And how many validation engineers are required? So he is going to design everything. That means how much time period is it going to require in order to do the project. For example, he is expecting that 12 months of duration it is needed to complete the project. So among these 12 months, within 2 months, design has to be completed. Within 3 months, verification has to be completed. Within 4 months, validation has to be completed. So he is going to design everything related to the project. Okay, so how many engineers are required to complete the project, and how much duration is it going to take to complete each and everything. That means he is going to design everything. That means he is going to give the blueprint of the project. Okay, so for example, this needs 2 design engineers and 8 verification engineers. So GLS team should consisting of 3 members, and validation 4 engineers are required. So in that manner, he is going to design everything, and design should be completed within 2 months, and verification should be completed within 3 months, and validation should be completed within 4 months. So he is going to design everything related to the project. Okay, so once it is done, next one is,
Sir,
yeah,
along with if they're working with a project, there if there are available pre-design modules,
pre-design
they can
modules. Yeah.
use. Yeah,
Ah,
all those things we can use this in the current
yes,
project also.
yeah, we can use it. That we call it as a reusability. Okay, so for example, see, one mobile phone is already there. Okay, that means the chip is already there. So
Yes,
but
sir.
I need some other advancement. For example, the chip is working with see, one type of application. The chip, for example, let's correlate with the general usage. The chip is working with 4G speed. So now what you have to do, you wanted to upgrade it to 5G. It has to support the 5G speed, right? So now what you have to do, so you don't need to develop everything from the scratch. Okay, so whatever the things are available for the 4G, you can reuse the same things to develop the 5G as well. So you
Yes,
can
sir.
take the same chip again. That process we call it as reusability.
Sir,
And
somewhere I'd read that reusability concept, what you are saying now,
mm,
those things also will be included in this architectural planning.
architecture planning. So he is going to decide everything, right? So for example, so this is my requirement. So my chip has, my processor has to work with the 5G mode. So already some
Yeah.
4G model is available with me.
Yes,
So
sir. Optimized.
he is going to design the thing. That means already as I have 4G model, then what I need to do, I have to make it to the 5G enabled. So I need one design engineer to do the upgradation. Okay. So in order to do this, I may need only 2 months of time. Okay. After that, one person must be there in order to verify that. So that roles we are going to discuss. So he is going to design everything. That means what are the sources already available with me? What are the other sources I need to bring it into the project to make it as early as possible? Because in the market, always some competition will be there. So whoever releases the first, they will get more profit, right, Harshit?
Yes, sir.
So
Time to market.
yeah, so time to market, that is a major thing in marketing the things,
VLSI.
right? So he is going to decide everything. So what are the resources I need? Okay, what are the already available things I have? Okay, what are the other advancements I need to require? So in order to meet the client's requirement, so all these things he is going to design. That is why we call him as the architect. He is going to architect the entire project flow. Okay.
Okay,
uh,
sir.
yeah, so now once he get the entire blueprint, okay, that means how many design engineers are required, how many verification engineers are required, and how many other engineers are required, and what are the time taken to do everything. Now the design engineer will come into the picture. Okay, so what this design engineer is going to do, he is going to develop design engineer or RTL engineer. So why do we call it as an RTL? That I will discuss later. Okay, so the design engineer or RTL engineer, what he is going to do means, he is going to develop the functionality by hardware description language. Okay, so guys, now we will come to know what is the difference between this hardware description language and software language. Okay, so this HDL means hardware description language. Okay, so the difference between software language and hardware description language is, okay, so by using softwares also we can develop some coding, And by using hardware description language also, we can develop some coding. But the difference between software and hardware description language is whatever the code that we are going to develop by using software languages, that means it can be C, C++, Python, Java, or any software language, that cannot be implemented at physical level. Okay, so whatever the code that you are going to write by using software languages, that means we are going to use some key constructs, right? So constructs means nothing but fundamental keywords that we are using in that language. For example, if we take C language, okay, some printf, that is a keyword, some scanf, that is a keyword, array is a keyword, right? Void main is a keyword, and stdio.h, that is a keyword. Okay, so all these keywords we cannot be implemented at the hardware level. That means at the physical level, you cannot implement all these things. So in order to execute these things, we need some tools. Okay, so in order to execute the functionality of this coding, we need some tools. That means by using some software, tool means nothing but a software. So the software is going to convert this code into an executable format.
Compiler?
Okay, sorry?
Is it a compiler?
Yes, I mean, tool consisting of lot of things. Among that, compiler is one of the things.
Okay, sir.
Okay, so tool means nothing but a software, Harshit. So in that software, compiler is a part.
Okay, sir.
Okay, so even in our HDL also, I mean, whatever the tools that we are going to use in this hardware description language, also compiler is there. Okay, so every programming language has some compiler by default, because these programming languages cannot be understood by the processor. It can understand only two things, binary, either 0 or 1. So what you need to do, so you have to convert that into I mean, programming language into machine understandable language. So there are some 5 to 6 steps are there in the conversion from programming to machine understandable language. Among those processes, compilation is one of the process. That job will be taken care by compiler. Okay, so now what this tool is going to do, it is going to execute this thing. Execution means nothing but, so whatever the functionality we would like to get from this coding, are we getting the same thing or not? That process, we call it as an execution. So we are going to run the program. I mean, in C language, you might have seen this one. So we are going to run this program. So are we going to get the proper output or not? That process, we call it as an execution. Okay, so in order to execute the functionalities, we need some tools. And this coding we cannot implement at the hardware level. In a physical form, you cannot be able to implement this one. But hardware description language, the name itself saying that hardware description. That means how you want the hardware chip to behave. Okay, so it is going to describe the hardware behavior. This language is going to describe the hardware behavior. So all the constructs or keywords that we are going to use in hardware description language are, most of the constructs are hardware implement, physical implement. Okay, so synthesizable is a keyword. Okay, that means the constructs that we are using in our, okay, can be implemented at relevant to the hardware or physical implementation. But software things you cannot implement it at the physical level. Okay, so that is why we call it as hardware description language. That means it is going to describe the behavior of the hardware, how it needs to behave, what kind of functionality it needs to execute. Okay, so all these things are physically implemented. All these things can be physically implemented. 95% of the constructs are physically implemented. That is the difference between software languages and hardware description languages. Software languages cannot be implemented at hardware level, but hardware description language constructs can be implemented at the hardware level. Okay, so design engineer, what he is going to do, so he is going to develop the functionality of the specification. That means, for example, client comes up with a specification. That means I need to execute this type of functionality. Okay, so how you
Yeah,
can,
I want to add one more point about hardware and hardware language and software.
yes,
So
please.
what about the concurrent execution and sequential execution?
Concurrent execution means,
We can add this point too for hardware and software also. Right?
yeah, so we can add all these things, but this is not the right time to explain everything,
Okay, okay, okay,
because
okay,
this is a
okay.
demo session, right? So when we come across with the Verilog and system Verilog, we can add all those points. So this is not only the one point. So there are some 5 to 6 differences are there. Okay, between
Okay.
software language and hardware. This is just to give you an overview about these things. This is a demo session, right? So when it comes to a regular class, I'll explain everything to you, Harshit. So concurrent execution and sequential execution means, see Harshit, in sequential execution, for example, if you have written 4 lines of code, okay, now the simulator is going to execute everything one by one. That means once it completes the first line, then only it is going to the second line. If it doesn't finish the first line, it will not go to the second line. And once it finishes the second line execution, then only it will go to the third line. Otherwise, it won't execute the third line. That means the execution of the below statement is dependent on the previous statement. This type of execution, we call it as a sequential execution. That means one by one execution. Concurrent execution means,
Parallel execution.
exactly. Okay, so the execution will start, the execution of all the statements will start parallelly. And finishing of that execution, it depends on the logic that we have inserted into the line. For example, the first line might take only lesser time period to execute, but the second line might take some more time. Okay, so depending on the logic that we are going to include in the lines, it may take its own time to finish its execution. But the starting of these executions, will start parallelly. Okay, so the execution of one statement is independent of the other's execution. Okay, so it doesn't need to wait for the first one. But in case of sequential, if the second statement has to be executed, it must finish the first statement. That means the execution of the second one is dependent on the first one. But here concurrent, so there is no dependency of execution of one statement on the other. All the statements will start their execution parallelly. That is the difference between sequential and concurrent. Right, Harshit? Is
Yes,
it
sir.
clear?
Yeah.
Yeah.
Clear, clear.
So now, design engineer is going to develop the functionality by using hardware description languages. So what are those hardware description languages means? Verilog is one of the hardware description language, and system Verilog is another hardware description language. Okay, so this is hardware description and verification language. Okay, so both the things can be done by using system Verilog, but most of the constructs of Verilog are hardware description, and most of the system Verilog constructs are hardware verification language. Okay, that means most of the system Verilog is used to verify the design. Most of the Verilog is used for describe the behavior of the design. Okay, and one other language is also there, VHDL. So these are the hardware description languages. So by using these constructs, design engineer is going to develop the functionality of the specification. Okay, so that means he is going to develop one code, okay, in order to meet the functionality. So the once he done this design part, what it is going to do? So it will be sent to verification engineer. Okay, so that RTL code or the design code will be sent to the verification engineer. Okay, so this verification engineer is going to get two inputs. One, RTL from the design engineer, and another one is the same specification he is going to get. So what is the responsibility of this verification engineer? That means our domain, design verification domain. So what is the main responsibility of this verification engineer is he has to check the correctness of the RTL code. That means design engineer is going to develop one coding file, right? So is that coding file executing the functionalities that are mentioned in the specifications in a proper manner or not? That he needs to check. He needs to check the correctness of the RTL code. That means whatever the code that is being written by the design engineer is correct or not. So is that code meeting the specification requirement or not? That is what he needs to verify. Okay, so for example, he has developed some edition functionality. Then what you need to do, so in order to check that functionalities, you have to give some inputs to that for that functionality. For example, if the edition functionality has been described in this manner, C equal to A plus B. If he developed in this manner, then what you need to do, so you have to provide some values for A and you have to provide some values for B. After that, you need to check this value, C value. If it is 25, then this functionality is working fine. So other than 25, if C is being calculated some other value, that means this functionality is wrong. That means design engineer, he is not coded in a proper way. So you have to give that information to the design engineer that this functionality is not working fine for the inputs. So you have to modify your design code. In such manner, he has to give the feedback to the design engineer. So what you need to do, so you have to analyze the correctness of the RTL code. You have to check the code, whether it is working fine or not. That is done by verification engineer. And one more thing, this verification engineer is going to deal with the functionalities, only functionalities. Okay, so in the specification, so specification might include all these things: frequency, power consumption, IO pins, size of the chip, and clock signal requirement. So it is going to consisting of all these things, but these functionalities only be checked by verification engineer. That is why this verification engineer also be called as functional verification engineer. That means he will check only the functionalities. He is not going to take care of the remaining things. Okay, whether all the functionalities are working fine or not, he is going to check it. The remaining things, he will not check it. Okay, so once the functionality wise, the chip is working properly, then it will be go to GLST. Okay, so if you find that, so being a verification engineer, it's your responsibility to check the correctness of the code. So once you find that the design is working fine, what you need to do, so you have to send that RTL code to the GLS team. GLS means gate level synthesis. GLS means gate level synthesis. So gate level synthesis means, so design engineer has developed some code to represent the functionality. Okay, so he has written some code by using hardware description language. So what it has to be do, so in gate level synthesis, this code will be converted in terms of gates. This code, whatever the code that is being written by the design engineer, will be converted in terms of gates, some logic gates in this manner. Okay, so in forms of gates, you are going to represent the behavior of the functionality. So in RTL coding, what you are going to do, you are going to represent the functionality in terms of coding. In gate level synthesis, what you are going to do, so you are going to represent the functionality in terms of gates. Okay, so we have some gates, right? NAND gate, NOR gate, XOR gate, AND gate, OR gate. So all these things. Okay, so you are going to represent the functionality in terms of gates. So this
Like
process,
in the form of structural level of modeling.
yeah, exactly, structural level of modeling. So in gate level synthesis, what you are going to do, so you are going to convert the RTL coding into structural format. Okay, that process of converting, we call it as synthesis process. Okay, so some tools are available in order to convert this. For that tool, what you need to do, you have to give the input as RTL. Okay, so it is going to convert the RTL code into structural format or in terms of gates. Okay, so now you have to check the behavior of this gates representation. Okay, so the functionality you have verified in terms of RTL code. So here the verification engineer is going to check the correctness of this RTL code. Now again, once you convert them into gate level netlist, okay, or into the structural format, you have to verify it again, because it is working fine in terms of coding, but you have to check it in terms of gates as well, because on the physical chip we are not going to have any coding format, right? So we are going to design the thing in terms of structures. Okay, so we are going to implement the functionality in terms of gates, in terms of transistors, in terms of capacitors. So all the physical components we are going to use it. Okay, so in physical format, how it is behaving, guys, remember one thing, till now we have not manufactured the chip, we are just assuming the things. So if it is converted into a physical format, how it is going to behave. Okay, that is what we are going to do in GLS domain. Okay, so if you convert the coding into physical format, how it is going to work like. Okay, that is what we need to do. So here also in GLS team also we are going to verify it again. Verification, we have to do it again. Okay, so once you convert into structural format, how it is behaving. So you have to do all these things. So these are GLS team also we are going to verify the things again. Okay, so that means structural verification. So these are the domains of front end. Okay, so all these things we are describing under the categories of ASIC flow. That means if the chip has to be designed, what are the things it has to go through? What are the domains it has to go through? So that is what we are discussing about, and this is front end. Okay, so the back end we will discuss. So guys, so now the time is 11:15. You take break for 15 minutes. Okay, so after completing the break period, we will discuss about the remaining things. Okay, so till now we have discussed about the front end domain. After the break period, we will discuss about the back end domain. So guys, whatever the things that we discussed, is it clear to everyone?
Sir, that GLS will be done by verification engineer, or there will be separate team for that?
Actually, we cannot say that, because in some of the companies, separate GLS team will be there. So they are going to do the verification. But in some of the companies, for example, if verification engineer is an experienced one, that means if he has an experience, more than experience of 12 years or 15 years, sometimes they know how to do that in structural format. Okay, so we cannot say that whether it is a combined one, or are we going to have a different team to do that.
Okay, sir. Thank you.
Okay, so it is it depends on the company. So if you're joined as a fresher, you're not going to do anything with the GLS. But if you get some experience, if you are interested to go to that domain, then you can learn it. And being a verification engineer, you have to verify it functionally, that means on the RTL part, you have to do the verification. And after that, if you are interested, you can do it at GLS level as well.
Okay, sir.
Yeah. Okay, yes. You take break for 15 minutes. We'll resume the session at 11:30. So post that, we will discuss about the backend. Okay. Okay, guys, so let's resume the session. So this is the front-end domain. So in the front-end domain, all these engineers are present. So let us come back to backend. That means once the GLS teams ASIC flow backend. So from the GLS team, they are going to have the structural form, right? And they have verified the functionalities, right? Now, from the GLS team, they are going to get the netlist. Okay, so this netlist will be forwarded to DFT team. DFT means design for testability. And this netlist will be forwarded to validation engineer as well. Okay, so in the DFT team and in the validation team, so what they are going to do means, so DFT team so the functionalities have been verified in verification domain, as well as in the structural format they have verified by the GLS team as well. The remaining things will be verified in the DFT team. Okay, so in the DFT domain, the remaining things, that means in the specification, the client is going to mention all the required things, right? So the frequency, power consumption, IO pins, clock signal requirement. So all the remaining things, the power consumption and the memories. Okay, so the chip is going through different test patterns by the DFT teams. So in order to test the IC for different scenarios, they are going to use some ATPGs, automatic test pattern generation. Okay, so they are going to use automatic pattern generation. That means automatically different test scenarios are going to be created to verify the IC. So not only the functionality, rather the remaining things also going to be verified by this DFT team. Okay, so the memory insertions, so all these things are going to be verified through DFT team, design for testability. Okay, only the test is going to happen. And what is this validation engineer is going to do? So this validation engineers, actually there are two validation roles. One is pre-silicon validation. One is pre-silicon validation. And another one is post-silicon validation. Okay, so in the pre-silicon validation and post-silicon validation, the IC will be go through different scenarios. Okay, so what are those scenarios? This IC will be tested for different temperature conditions. This IC will be tested for different pressure conditions. This IC will be tested for some different physical conditions. Okay, so under all these conditions, that IC has to behave in a proper way. So whether it is behaving in a proper way or not, it is going to be checked in the validation part. Okay, so validation engineer is going to subject different physical conditions to the ICs. Under all these conditions, IC has to behave. That means he is going to generate a report which states that for 25 degrees of temperature, how the IC is behaving. So he is going to increase the temperature 25.1 degrees, how the chip is behaving. And for 25.4 degrees, how the chip is behaving. For 30 degrees, how the chip is behaving. In the same way, he is going to decrease the temperature as well. For 24 degrees, how the chip is behaving. For 23 degrees, how the chip is behaving. And for 1 Pascal, how the chip is behaving. And for 1.1 Pascal, how the chip is behaving. And for 0.9 Pascal, how the chip is behaving. So in such a way that he is going to subject different physical conditions for the IC. And under all those conditions, how this IC is behaving. So he is going to generate a report based on that one. Right, guys? So along with these things, what it is going to do, along with these things, okay, so and different physical conditions are also be subjected to this ISIS. Okay, so I told you, right? So there are two validation roles. One is pre-silicon and other one is post-silicon. So pre-silicon refers to before manufacturing the chip. Before manufacturing the chip. And post-silicon means after manufacturing the chip. So pre-silicon means before manufacturing the chip. Post-silicon means after manufacturing the chip. Okay, so validation is going to be conducted in both the in both the times. Okay, so before manufacturing chip, how the chip is behaving under different physical conditions. After manufacturing the chip, how the chip is behaving under different physical conditions. So after manufacturing the chip, we can subject the chip to different physical conditions. That means physically you can increase the temperature or decrease the temperature. Physically you can increase the pressure or decrease the pressure. But before manufacturing the chip, how the chip is going to be validated for different conditions. That means they are going to use some tools. Okay, so they are going to use some tools in order to analyze these behaviors. Okay, so by using some software tool, he is going to increase the temperature and decrease the temperature. By using some software tools, he is going to increase the pressure and he is going to decrease the pressure. In that way, the different physical conditions are going to subject to IC, that means chip, by using some software tools. That process we call it as pre-silicon validation. So after manufacturing the chip, that means into the physical form, so this IC is going to be subjected to the physical parameters manual. Not using by software tools, they are going to be implemented in a physical form. Okay, so physically they are going to increase the temperature and decrease the temperature. Physically they are going to increase the pressure and decrease the pressure. Okay, so in pre-silicon they are going to use some tools, and in the post-silicon they are going to use they are going to do everything physically. Okay, so after getting the netlist, the netlist will be forwarded to DFT team and validation team. So in the DFT, what they are going to do, so the IC is going to subject it to different test patterns in order to validate everything. Okay, so not only the functionalities, the remaining things also going to be verified by the DFT team. And in the validation team, in the validation domain, what they are going to do, they are going to analyze the behavior of the chip under different physical conditions. Okay, so once this is done, it is going to PDT. That means if you find that everything is working fine, then it will be go to PD team, physical design team. That means you verified the chip, you verified the netlist properly. That means at the structural way, it is behaving in a proper manner. Now you have to place the things in a chip. That means physical design. You have to design the chip in a physical way. Okay, so in PD domain, what they are going to do, how to integrate number of cells. Cell can be related to, cell refers to a combinational circuit. Cell means a combinational circuit or a sequential circuit, or it can refer to a transistor, or it can refer to a capacitor, or it can refer to a gate. So any physical circuit, we call it as a cell. So they are going to decide, so how many cells we have to use in order to get the required functionalities. So in the structural format, we are, in a structural format, we have verified it, right? So in order to implement this behavior, in order to implement this structural behavior, how many cells do we need to use? Okay, so in order to get the functionalities, in order to get the requirements, how many cells we need to use. Okay, and they are going through
Sir,
some optimization techniques. Yes, Harshit.
sir, where will I apply that constraints in which steps? In PD or
Constraints.
DFT?
1 minute.
Like
So
clock?
constraints means in which context you are asking?
Sorry, if it is it's like a sequential circuit, we need to apply clock for the design, sir.
Come again.
Frequency for fixing the frequency as specification mentioned.
Actually, frequency constraints are going to be applied in a CTS domain. That means clock tree synthesis. Okay,
Okay, sir.
so
Okay.
after doing this PD, we will move. There is one more domain, that is routing, placement, and routing domain. After that, we will move to the CTS domain. There, I will explain it. Okay,
First step
so
of
this
PD is
PD.
floor planning, sir.
Sorry.
First step of a PD is floor planning.
Not full floor planning. They are going to decide how many cells they have to use in order to get the requirement. Okay, so
Okay.
they are not going to organize everything. First, they have to decide. That means, for example, in order to construct any building, you need a plan, right? That means this much of raw material is required, and this many times, this many months of time is required. Like that, you are going to design everything, right? In the
Yes, sir.
same way, in order to get the requirement, how many cells do we need to use?
Okay.
Okay, so without compromising the functionality and without compromising the user requirements, how can we minimize the cells usage? Okay, so they are going to do that one. So they are going to implement a number of optimization techniques in order to reduce the number of cells. Okay, so after this, after PD, one more domain is there, that is placement and routing. Okay, so placement and routing means, so in PD domain, they will come to a conclusion. That means these many cells have to be used in order to get the functionality, right? So after that, what they are going to do means, they will do the analysis for the placement of the cells. That means, for example, so we have a constraint, right? That means the size must be within this range, within this limit, right? So without compromising on the size of the chip, how the cells have to be placed. For example, one cell has to be placed here, and another cell has to be placed here, and another cell has to be placed here. That means placement is going to be decided in this domain. So in the PD domain, from the PD domain, they are going to get one confirmation that, for example, these many number of cells have to be used. Number of cells has to be used in order to get that requirement, and how these cells have to be placed on the physical chip. Okay, so we have one constraint on the size of the chip. That means the size of the chip must be within these limits. It should cross that limit. Okay, so without compromising on the size of the chip, in order to get the best out of it, that means in order to get the less power consumption, in order to get the best performance, how the cells have to be placed. Okay, that is going to be decided by placement team. Okay, so they are also going to use some tools. Okay, and they are also going to going through some optimization techniques, how these cells have to be placed on the chip without compromising on the size of the chip. So the size of the chip should not be changed, because that is mentioned already there in the specification, right? So the number of cells is also be decided by the PD team. So the number of cells is fixed and the size is fixed. But in order to place these number of cells, in order to reduce the power dissipation, in order to reduce the power consumption, how the cells have to be placed. So the cells can be placed in any manner, but in order to get the best out of it, how these cells have to be placed on the chip, that is going to be decided by this placement team. And the next one is routing team. So routing means nothing but signal propagation. That means how the wires have to be arranged between the cells. Okay, so we should not get any problem, and we should not face any problem while transmission of the signals from one module to another module, or from one cell to another cell. Okay, so in order to avoid the losses and in order to avoid the propagation losses, how the routing has to be done. Okay, how the signal propagation has to be done with using of a proper wire. That means all the cells are connected properly or not. Is the information flowing properly from starting point to end point or not? Okay, that means whether all the connections have been made in a proper manner or not. For that one, what they are going to do, they will send some sample information from the input side, and they will check, are we getting the same information whatever we have sent at the output end or not. That means they are going to check the routing scheme. That means, are the all signals routing properly from one cell to another cell or not? Are the connections made properly or not? So that is going to be checked by this routing team. Okay, so once this is done, it will be sent to CTS, clock tree synthesis. So in clock tree synthesis, so they mainly focus on two things. One is clock signals, and another one is frequency. So the frequency requirement is going to be met here. Okay, so the frequency consideration, whatever that is mentioned in the specification, that will be met here. And what is meant by clock tree synthesis? Tree means it is going to split up the things, right? See, so in subsystem, many modules are going to be integrated with each other. So let us consider this is subsystem. And in these subsystems, there are many systems, many modules are there. Now, see, so whenever you are integrating, so integrating means making connection between all these modules. Right. So this module might be working with one type of frequency, and this module might be working with another type of frequency. And F2, F3, and F1. Let us consider these two modules are working with the same frequency, and these two modules are working with the same frequency, and these two modules are working with the same frequency. But are you going to give different clock pulses for all these modules? No. From processor is going to, okay, so processor, our main controller, is going to generate only one clock signal. Okay, so that clock signal has to be supplied to all these modules, but all the modules are working with different frequencies. So let us consider one example. So processor has generated some clock as 32 Hz clock. Okay, so this clock has a frequency of 32 Hz, and this module is working with 32, and this module is working with 16, and this module is working with 8. In the same way, this module is working with 16 Hz, and this module is working with 8 Hz, and this module is working with 32 Hz. That means different modules are working with different frequencies, but processor is going to generate only one clock signal. So that clock will be given to this subsystem. Now what it has to do, this has to be provided as it is to the module 1. But this module is working with 16 Hz. But what is the input signal that we are getting? 32 Hz we are getting. But what is this module is working with? It is working with 16 Hz. That means what you need to do? You have to do frequency division. So these modules, we call it as synthesizers. Synchronizers, sorry, synchronizers. Not synthesizers, synchronizers. So synchronizers means it is going to synchronize the input frequency with the module frequency. Okay, so frequency dividers are going to be implemented over here. This frequency division and frequency scaling, you might be learned in digital electronics. Okay, so some flip-flops and some counters we are going to use in order to divide the frequency. And the same type of synchronizers we are going to apply here as well. Because this module is working with 8Hz, but what is the input frequency? 32Hz. Okay, so divide by 4 synchronizers are going to use. Okay, in the same way, one main signal will be there, 32Hz. So from 32 to synchronizers. And this is divided by 4 synchronizer. And this is as it is. That means, why do we call it as a clock tree? Means we have one main branch and some sub branches. So let us consider this is the main branch and this is the sub branches. And for these sub branches, we have also have some other branches, right? In a tree. In the same way, the main clock that we are getting as 32Hz. So this 32 might be splitted into in this manner, 8 megahertz and 8 megahertz and 8 megahertz. That means before going to the sub branches, frequency divided by 4 synchronizers are there. And some modules might be working with 4 megahertz and some modules might be working with 2 megahertz, 2 hertz, and some modules might be working with 1 hertz. That means the input frequency 32 hertz will be going through number of paths, and finally to what frequency it has got? 1 Hz frequency. So as the frequency is getting split up into number of parts, we call it as clock tree synthesis. Okay, so in a tree manner, the clock is going to be divided into number of parts. Okay, so in order to do those things, we are going to use some synchronizers. Okay, so we face this situation very frequently when we integrate multiple things together. Okay, so this job is very, very important because multiple modules are going to work with multiple frequencies. So how you are going to divide the main input frequency into number of parts, and are we supplying the proper frequency to each module or not? So they are going to take care of these things. Harshit, is it understood now?
Yes, sir.
Hello?
And all the modules should, sir, understood. And all the modules, the clock should reach simultaneously, na, sir.
Yes,
Without
I
any
mean,
skew.
not simultaneously. There is one more controlling point is there, that is power controller. Okay, so everywhere we are using this power controller to avoid the unnecessary wastage of the power. That means, for example, see the example
Like
is here.
clock
This
gating technique
we are
almost,
using 6 modules.
clock gating technique?
Sorry? Yeah, clock
Means
gating
a
technique.
clock gating.
Exactly.
Yeah. Okay.
Exactly. So before giving the power supply to this module, we are using clock gating or power gating. Okay. So whenever this module requests some power, then only the processor will give the power to this module. Otherwise, this module is not going to get the power. So why they are implementing this power gating things are to avoid the unnecessary wastage.
Power dissipation.
Okay.
Unnecessary power.
Power dissipation, unnecessary power dissipation. So once all these things are done, then finally it will go to the manufacturing. Okay, so these are different domains are available in ASIC flow. So first you get the specification. After that, the design architect is going to plan everything for the project and how many engineers are required. After that, the functionality will be developed by the design engineer. After that, verification engineer is going to verify that. Once he verified successfully, then it will be go to synthesis team. That means they will convert the coding part into physical part, gate level netlist, structural format. So once that is done, it will be again sent to DFT team and validation team. So the chip will undergo through different tests. Okay, so both in physical format and along with some other things that the chip has to meet. So whatever the specifications that are listed, so for all the specifications, different tests will be generated and chip has to go through all those tests. Once it is done, for planning. That means how many cells do we need to use in order to get the functionality. After that, placement stage, how effectively we can place the things in order to get the best out of it. And clock synthesis and routing stage and final verification. That means I told you two things, right? There are two validation roles, pre-silicon validation role and post-silicon validation role. So once all this done, they will check it again at the final verification. So if the chip passes that stage as well, it will directly send to the factory. Okay, so GDS2 means, here the chip is going to be manufactured. Okay,
It's a file
so
format
this
now,
is,
sir.
sorry?
GDSI is a file format now, sir.
This is not a file format. GDS means a graphical data structure in information interchange. That means
It will be the
that
result will
means
be comes at the end of tool itself, no, sir.
result will be
After that GDSI is a file format which will comes after doing the clock synthesis and all after the PD class.
yes, exactly. So once the chip has gone through all these stages, the final report will be sent to the manufacturing unit, and there everything is mentioned. Okay, based on that, by using some automation and robots, they are going to manufacture the chip. Okay, so these many domains are available. So you need to decide whether to choose a front end or back end based on your interest. Okay, so among the front end domains are RTL design, functional verification, and formal verification. So formal verification is another type of verification. So this is not the right time to discuss about it. And when it comes to back end domains, for planning, placement, clock tree synthesis, routing, static timing analysis. So static timing analysis means some timing constraints has to be met. Okay, so you might have already learned what is the setup time and what is the hold time. So some timing constraints must be met in order to get the stable behavior from the chip. Okay, and the physical verification, I told you, right? Post silicon validation. That means after chip manufactured, it has to go through some physical tests. That verification we call it as physical verification. So in the front end domain, these
sir, in physical verification, you have mentioned some
Harshit, your
temperature.
voice is breaking. Yes. Not only temperature, some physical conditions. See, once you manufacture the chip, it has to give the best out of it under all the conditions. For example, if you take your mobile phone to the South Indian states, the temperatures are very high, right? But if you take your mobile phone to the North Indian states, the temperatures are very low. But at both the conditions, it has to give the same behavior.
All those physical
Right,
conditions
Harshit?
are created in the lab only, sir?
All the physical conditions.
Are created in lab?
Yeah, those are created in lab. Yeah. So
Okay.
see, the validation engineer, what he is going to do means, in the pre-silicon stage, one software will be there. So the software, whatever the netlist that they are getting from GLS team, they will put this netlist into, they will give that netlist to the software. Okay, so that software is going to create different conditions, and it will give a report how the chip is behaving under different conditions. Okay, that is pre-silicon stage. Post-silicon stage means in the lab, the chip is undergo through different conditions. That means they are going to increase the temperature physically, and they are going to decrease the temperature physically, and they are going to increase the pressure physically and decrease the pressure physically. In the same way, they are going to subject all these physical conditions in the lab, where in the post-silicon validation, once the chip is manufactured complete. But in the pre-silicon, by using some software tools, they are going to analyze everything. Understood?
Okay, sir.
Yeah. So guys, so which one is better? That depends on Your wish. Okay. So see, so in the front end VLSI, deals with logic design and functionality of the chip. That means we mostly go with the coding. Okay. But in the back end VLSI deals with the physical implementation of the chip. Okay. That means in order to bring the chip into physical format, what are the things that you need to do? Okay, so the main goal in front end is ensure circuit works properly or not. That means you are mainly focusing on the functionality. But back end means whatever the functionality that you have written through the coding, are you getting the same functionality when it convert that into manufacturer layout? That means in a physical format, when you convert that, are you getting the same functionality? Are you getting the same behavior or not? That you need to check in the backend. Okay, so focused area in the front end is design and verification, but in the back end, physical design. That means how capable you are implementing it in a physical form. And what are the languages that we are going to use in front end? Verilog, VHDL, and system Verilog. But in the back end, we are going to use Pickle languages, Perl language, Python language, and some other tools. Okay, so the important skills that you need if you want to get a job in front end means you have to be strong with digital electronics and coding and verification. So verification is also done by coding. Some system Verilog and UVM coding we are going to use. But if you want to get job in backend, you need to have a skills of for planning. That means optimization techniques. That means you have to think in an optimized way. Okay, so how effectively I have to optimize the things. I have to reduce the number of cells without compromising of the specification. That means you have to go through a smart thinking. Okay, so if you want to get it job in backend and routing and timing closure. Okay, so what are the tools that we are using? I mean, for both front end and back end, we are going to use the same tools, but the usage of the tool will be different. Okay, for coding, we are going to use the tool in one way, but for placement and routing and design, we are going to use the same tool in another way. So there are some versions, we are going to use those versions. Okay, so now, which one, if you ask me which one is better means, so if you are good at coding, you can go with the front end. Okay, but if you are interested in chip implementation, if you are more tool oriented, that means you can be able to utilize the tool in a proper way. Okay, you can utilize the tool in an effective way. You can optimize the things in a better way. Then you can go with backend. So if you are good at coding, you can choose front end. And you have to debug it. Debugging means nothing but, for example, if you are finding any errors in the design, you have to identify that one. Okay, so why that error is coming and which one is causing that error. So if you are analyzing all these things, that process of analyzation, we call it as debugging. Okay, so if you are good at finding the mistakes, then you can go with front end. Okay, so if you are good at optimization things, you can go with backend. Okay, so depending on the interest, you have to choose the correct domain. And as I told you, RTL design means RTL means register transfer level. That means during between some registers, some data is going to be transferred. That behavior you have to explain it to. Yeah.
Sir, more vacancies available in front end or back end, sir?
Actually, we cannot say that. But one thing I can say that for one RTL engineer, we need 4 verification engineers. Okay, so in the front end, there are 4 domains, right? So for one RTL engineer, we need 4 verification engineers because finding the bug is very, very important at the earlier stages. Okay, so we cannot say that in which domain more opportunities are there and in which domain less opportunities are there. So as I told you earlier in the starting of the session, in every domain, equal opportunities are there. So you don't need to worry about it. So in the design verification, we have more vacancies, and in the same way, more competency is also there. Okay. So
Okay,
if you,
okay, sir.
I mean, if we observe the registrations for different domains, for PD, we come across with 30 or 40. Okay. And for layout, we come across with 20 or 30. And for in the same way for other domains also, we come across the registrations as 20 to 30, in between that range. But when it comes to design verification, we have got the registrations for 100 to 150 members. Okay, so opportunities are high and also competency is high. Okay, so we cannot say that. So my suggestion is always go with your interest. Okay, so if you go with your interest, obviously your passion will be more to learn something. So if the interviewer find the passion, that passion in you, definitely he is going to consider you. Okay, so even there are more opportunities. If you are not good at coding skills, then he might not take you. Right. So always go with your passion. Based on your interest, you have to choose your career. We cannot say that in this domain you have to choose because of more opportunities. In this domain, you are not supposed to choose that one because of the less opportunities. Always equal opportunities are there for every domain. And one more thing, let me tell you. So you are going to have the demand not only in India, we have the requirement across the globe. Okay, so even in abroad also we have huge requirement for the VLSI engineers. Okay, so always take a step based on your passion. Okay, so now if it comes to a design part, what RTL explains how the data is going to move between the registers and what operations are performed on the data. That means what is the functionality you need to execute upon getting the data. Okay, and how the circuit is going to behave with the clock and control signals. So these are the functionalities are going to be mentioned inside the design. So your responsibility. So being a verification engineer, what is your job? You have to verify the correctness of the design. Okay, so the design verification is the process of validating the design functionality. Is the functionality working fine or not? That is what you need to check. Okay, so for the functional verification engineer, he is going to get two inputs. One is design specification and another one is RTL code. Okay, so this RTL code he has to verify. So is the code is behaving as per the specification or not? That you need to find out. So verification engineer's responsibility is to find out the bugs. Bugs means nothing but some errors. Okay, so if you find more errors inside the design, means you will be treated as a good verification engineer. Okay, and you have to find out the correct bugs, proper bugs. Okay, so it's your responsibility to verify the design. In order to verify the design, okay, so in order to verify the design, we are going to develop one component called test bench. Okay, so we will discuss about it. So what is the importance of verification? So fabricating a chip is extremely expensive, as I told you, right? So the IC is going to be manufactured when there is a requirement. Otherwise, you are not going to manufacture the IP. This is ASIC. That means application specific IC. IC is going to be manufactured only when there is a requirement. And that IC is meant for only that application. You cannot use that IC for the other application. So it is very specific. Okay, so when you are developing anything very specific to one thing, means it is extremely expensive. So you need to find out the bug as early as possible. So if a bug exists after the manufacturing, that means if it crosses all the stages, and after that you found the bug, means the entire time that you have invested and the money and the people's effort will be gone into vain. Okay, there will be no usage of spending this much of time and money. Okay, so you need to analyze the things at early stages. You need to find out the bugs at early stages. Okay, that is why we need verification. So once you develop anything, you have to check it. That process, we call it as a verification. Okay, so the verification should be done thoroughly before the fabrication. That is why we are doing the verification at functional verification domain and at GLS domain and at pre-silicon and at post silicon. At all these stages, we are verifying it. So we are verifying it thoroughly, whether it is working fine or not. Okay, so what are the languages you are going to use in the verification means? Verilog, system Verilog, and U. So by using all the things, you can be able to verify the design. Okay, so UVM is not a language, it is a methodology. Okay, so we will discuss in detail in the regular sessions. Okay, so UVM is not a language, it is a methodology. That means it is a part of system Verilog. Okay, so these are the things we are going to use in verification. Now, what is the role of a verification engineer? So being a verification engineer, what you need to do? So you have to understand the specification in a clear manner. What is client requirement? Okay, so based on that, you need to develop the test plan. That means what features have to be tested. Okay, so in the specification, he is going to mention some list of the features, right? So all the features, you need to develop a test plan. That means these many features I have to test. In order to verify these tests, I need this much amount of time. Okay, and what are the test benches I need to develop? So one component is there, that component we call it as a test bench. Okay, so by using this test bench, you are going to verify the design. Okay, and next one is test cases. Okay, which scenarios you have to develop in order to verify the design. That scenario we call it as a test case. Okay, and you have to run the simulation. Simulation means through coding wise, you are going to verify the functionality, right? So whenever you are dealing with the coding, you need some simulators. That means you need some software tools. Okay, so through the software tools, you are going to analyze the things. Is it behaving properly or not? That we call it as a simulation. And you have to find out the bugs. Bugs means nothing but errors in the design. And measure the coverage. So are you covered all the functionalities or not? So whatever the functionalities that are mentioned in the specifications, did you cover all of those things or not? And you have to ensure the design quality. So based on your certification only, the client is going to be satisfied with the product. Okay, so if you certify that the design is working fine, then only he is going to take that design. Otherwise, he won't take the design. So you have to make sure one thing, that design has to behave in a proper manner. And what is the verification flow overview? That means what is the flow of it? So once you get the design specification, design is going to be done. Okay, so once the design is done, it will be given to the verification engineer. Now, what he has to do? He has to build up one component. That component we call it as test bench. Okay, so through this test bench, you are going to verify the design. After that, you have to go through the simulation part. So the analyzation is going to be done in the simulation part. Next, bug detection. Bug detection means error. Bug means nothing but unintended functionality. That means an error. Okay, that you have to identify. So if it can be resolved earlier, then you can give the same RTL code to design engineer, and you have to convey the information related to that bug. And once it is resolved, then you will get back the design again. Okay, and you have to do the verification process on the updated one. Okay, so this is how you need to debug it. Debugging means nothing but resolving the error. Okay, so you have to make sure one thing, that design has to work properly. So whenever you find any error during the verification process, you have to give that information to the RTL engineer, and he will make some modifications. Again, he will send the updated RTL to you, and you have to verify it again. This process we call it as debugging. And you have to coverage. Okay, so coverage means, for example, in the specification, there are 10 features are listed. You have to verify all the 10 features. You should not skip any feature. Okay, so you have to find out the bugs in all the features, and you have to verify all the features. That process we call it as coverage analysis. That means you have to cover everything. And the final verified design, you have to give it to the GLS team. There, the RTL will be converted into the netlist. So this is the flow of verification. And So for joining design verification course, what are the prerequisites you need? So you need to have basics of electronics. Okay, so that you have already learned in BTech, and it's digital electronics. So we are going to deal with the digital things. So you need to learn the digital electronics. So if you're aware of all of these things, the course will be easier to you. So if you have any doubts, don't worry. We are going to teach you everything. So, but we are not going to cover the basics of electronics. You should have the basic knowledge about the electronics, how the mux is going to work, how the MOSFETs are going to work, how the JFETs are going to work. So you need to have at least the basic knowledge on the electronics. And if you're aware of digital electronics, the C language, because Verilog language is similar to C language. It is not same as the C, but it is similar to C language. So if you're aware of the Verilog C language, the Verilog language, you can learn it earlier. Okay, so in a fast manner, you can be able to understand the things. And if you are aware of OOPS concept, so in C++ and in Java, OOPS concept is there. So if you already learn them, the system Verilog language will be easier for you. Okay, and awareness of the text editors. That means we are going to write the code in one file, right? That file we call it as text editor. That means how can you edit the things in the coding file. And we are not going to deal with the Windows operating system. We are going to deal with the Linux operating system. Okay, so even if you go to the industry, they are also going to use this Linux operating system. Okay, so they are not going to use the Windows. They are going to use Linux operating system. And Verilog basics. That means during your 6th semester or 7th semesters, you might have learned something related to Verilog things, right? So if you know the basics of the Verilog, so when you come here, it will be very easier for you to understanding them. Okay, but if you don't know anything, but don't worry. Okay, so we will teach you everything, but the basic electronics we are not going to teach. You should have the basic knowledge about the electronics. Okay, so what are the things that we are going to cover in the regular session means Linux and GVim commands. I told you, right? So in industry, they are using Linux operating system. So in order to get familiar with that, we are going to teach you what are the Linux commands, how the operating system is going to work. Okay, and GVim is a text editor. That means you are writing the coding in a file, right? So in order to edit the things, what are the commands that you have, and we are going to teach you those things. And we will revise everything in the digital electronics. Okay, so Boolean algebra, number systems, combinational circuits, sequential circuits, finite state machines, everything we are going to teach you. Along with that, we are also going to teach you static timing analysis. Okay, and the RTL part. So being a verification engineer, what you need to do? So first you need to understand the RTL code. Okay, so whether it is working fine or not, you have to understand it, right? But in order to understand it, you have to understand the Verilog language. That is why we are going to teach you the Verilog. So in order to understand the RTL part, you have some knowledge on the Verilog language. So we are going to teach you the Verilog concepts, and after that, we will make you to do some projects on the Verilog. Okay, but Verilog is meant for RTL coding, not for the verification purpose. So for the verification, we use system Verilog and UVM, and those concepts we are going to cover. Okay, to familiar with those concepts, we are going to make you do some projects on system Verilog on UVM, so that you will get some hands-on experience on the system Verilog concepts and UVM concepts. So as I told you earlier, protocol means nothing but it is some set of rules. When it comes to VLSI domains, as we are dealing with the data transfers, how the data has to be transferred from one component to other component, it is going to be described by the protocols. Okay, this protocol, I mean, so if you aware of more than protocols means your resume, your credentiality for your resume will get increased. Okay, so protocols are very, very important in VLSI. Okay, so if you're aware of more protocols means the chances of getting shortlisted your resume will be more. Okay, so learn as many protocols as you can. Okay, and the next one is industry standard projects. Okay, And we also teach you Python scripting language. Okay, so why do we need this scripting language? It means in order to automate the things. Okay, so every time you cannot do everything by manually. So if it take, I mean, for example, if you have to do one thing, if it takes 10 days of time, okay, if you have to do it manually, if you make use of Python language, it can be done within 2 hours or 3 hours of time. That is the advantage of scripting languages. Okay, so if you have to do the same thing by manually, it is going to take days of time. But if you make use of the languages, scripting languages or automation languages, the same job can be done within 2 hours or 3 hours of time. That is the advantage of scripting languages. So Python is more usable in automation. So that is why we are going to teach you Python language. The next one is Verilog verification. That means the verification you can do it by using Verilog as well, but there are some disadvantages by using this Verilog language. So it is a hardware description language. That means most of the constructs are meant for RTL coding, not for the test bench. Okay, and we don't have any pre-implemented methods. Pre-implemented means the structure is already available. So like in the FPGA boards, what we have, we do already have the available breadboards. So along with the basic functionality, we are going to add up some additional functionality, right? In the same way, in System Verilog, we have some pre-implemented methods. That means the basic functionality is already defined over there. We don't need to develop anything from the scratch. But in Verilog, whatever you want to do, you have to develop everything from the scratch. So it is going to take a lot of your time. Okay, so this is not a good one for the verification. It is a good one for the RTL coding. For a verification engineer, System Verilog and UVM are very, very useful. Verilog also useful, but to understand the RTL code. Okay, so the verification can be done by using Verilog as well, but it is not the effective way. It is not a recommended way. That is why we are moving to System Verilog. Okay, so after Verilog, in order to understand the coding, that means how the design has to be analyzed, we are going to make you do some projects on finite state machines and single port RAMs. Okay, single port RAM means nothing but MMO. So once you get the RTL code, how you need to analyze the code. So to get experience on that, we are going to make you some projects on Verilog. And so I told you, right? So System Verilog and UVM are good for verification. So how effectively they are useful for the verification? Because of some of the concepts. So System Verilog supports some object-oriented program. So if you are aware of C++ or Java, you might have already gone through this object-oriented programming. That means through some classes and inheritance and polymorphism and encapsulation, all these things, what they are going to do is these helps to build the reusable verification environments. That means once you develop anything, you can use the same thing for other purpose as well. So once you develop the basic part, that basic part can be used for multiple things. That concept we call it as reusability. Okay, so once you develop anything, the same thing you can use it for multiple purposes. Every time you don't need to develop it from the scratch. That concept we call it as reusability. And that reusability can be achieved by using this object-oriented programming by having all these things. Okay, and constraint randomization. So in order to verify anything, you need to supply some inputs. But every time it is not possible to supply the inputs manually. Sometimes what you have to do, you have to randomize the things. Okay, so as I told you earlier, automation is going to play a very, very important role in verification, right? So in order to automate the things, you need to follow some things like constraint randomization. So every time you cannot pass the inputs manually. Sometimes you need to automate that one. In order to automate that one, this concept will be very used. Okay, so generates random test cases automatically. You don't need to develop it. Automatically, the test cases are going to be generated. So it is going to reduce the manual test writing and finds the corner case bugs. That means whatever the things that are not covered by using manual cases, those can be covered by using constraint randomization. Okay, so in order to analyze the yeah, is anyone calling me? Guys, did anyone call me? Okay. So in order to analyze the design behavior signals, we are going to use one more concept called assertions. Okay, so how the design signals are behaving, at what point of time, how they are behaving. In order to analyze those things, we need some assertions. So through these assertions, you can be able to find out the bugs in a lesser time period. And you can check the protocol. That means as they are following the rules or not. You can check it in a lesser time period so that you can debug it easily. That means everywhere you are reducing the time for the verification. Okay, and are you covered all the functionalities or not? In order to check that, we don't have any specific metric in Verilog. But in System Verilog, we have one metric called functional coverage. So through this, you will get to know how many functionalities that you have covered and how many are there in the specification. So whether you have covered all the things or not, that you are going to get by using this functional coverage. And in System Verilog, so if you see the System Verilog test bench, this is how it is going to look like. So we have some components like generator, driver, monitor, and scoreboard. So these are subcomponents of the test bench. So the main purpose of using test bench is to verify the design, whether it is working fine or properly. In order to verify that, we have to generate some test cases. In order to generate those things, we need generator. And in order to send them from the test bench to the design, we are going to use this drive. Okay, so these are the subcomponents of the System Verilog test bench. That means every component is going to meant for do some specific job. And how these components are going to be connected by using these things. Okay, so use it for communication between the test bench components. Okay, and we have some dynamic data structures. That means based on your requirement, you can change the behavior of those things. So we don't need to always stuck with the similar point of approach. Okay, so you can change the behavior as per your requirement. That type of behavior we call it as dynamic data structures. So by using all these things, as per your requirement, you can change the behavior of that thing. Okay, that means different test patterns you can generate. Okay, so that is how System Verilog will be very useful for to do the verification. Okay, so how we are going to do, we will discuss in our regular sessions. And once the System Verilog is done, we will teach you how to do the projects. That means how can you develop different test benches to verify the correctness of the different designs. So some RTL design files will be given to you. You have to verify those things, whether the functionality is working fine or not. So in order to get some experience, you have to go through all these things. So you are going to work with counter and comparator and ALU, basic functionality, interrupt controller, power controller, and you will be gone through some protocols as well. Okay, so these are the things you are going to do it. Harshit, as you asked me earlier, there are two protocols. One is on-chip protocol, other one is peripheral protocol. So let me explain that one.
Okay, sir.
I'll just give you a brief introduction about it. I'm not going to in detail about it. So protocol means, as I told you earlier, they are going to be useful for data communication. So let us consider this is the system. Okay, so let us consider this is the laptop. Okay, so inside the laptop IC, there are many modules are there. Okay, so these modules have to communicate with each other. And along with this thing, this IC modules have to be communicate with the IO devices as well. IO devices means peripheral devices, input-output devices. That means they can get the information from these devices and they can give, This IC can get the information from the output devices and it can give the information to these devices. That means both the data transformation can be available. It can take the information or it can give the information. That we call it as IO devices. So this IO devices can be keyboard, can be mouse, can be pen drive. Okay. So now protocol means it is going to list out some rules how the data transfer should happen. Okay. Now, if the data has to be transferred within the chip itself, so this is module 1 and this is module 2, and both the modules are inside the chip. So if the communication has to happen between these two modules, we are going with on-chip protocols. Okay, but if the data has to be transferred from second device to keyboard, or second device to mouse, or second device to pen drive, that means the communication is happening between the IC and peripheral devices. Then we go with peripheral protocols. Okay, so these are the two types of protocols, on-chip protocols and peripheral. If the data communication has to happen within the modules of the IC itself, then we go with on-chip. If the data has to be transferred from the chip to outside device, we use peripheral protocol. Now,
So UART
all
and SPI are peripheral, right, sir?
Sorry?
UART and SPI are peripheral protocol.
Yeah, I'm going to tell that. So on-chip protocols are AMBA protocols. AMBA protocols means APB, AHB, and AXI, CHI protocol. And in AXI, light version is there, third version is there, and fourth version is there. And some other protocols also there. So
ACE.
the acronym might says advanced peripheral bus, but it is not a peripheral protocol. It is on-chip protocol. Okay, that means it is used for the communication between two devices within the chip itself. Now, when it comes to peripheral protocols, UART, I2C, SPI, USB, PCI, SATA, Ethernet. Okay, some other protocols are. These are peripheral protocols. That means these are used to have a communication between the device that is there inside the chip and with the device that is outside the chip. Okay, so there are two types of protocols. These are the peripheral protocols and these are the on-chip protocols, right? Now, so even system Verilog has also some disadvantages. That means you have to develop everything from the scratch. But when it comes to UVM, you don't need to develop anything from the scratch. By default, everything will be there. So just like, for example, if you have to develop one system Verilog test bench, you have to develop the generator from the scratch. You have to develop the driver from the scratch. You have to develop the monitor from the scratch. But in UVM, for every component, default libraries are available. By default, one generator class will be there. By default, one driver class will be there. By default, some scoreboard class will be there. So for everything, one default class will be available. That means you don't need to develop anything from the scratch. For everything, you have one thing in by default. That is the advantage of UVM. That is why every company is going with this type of approach, universal verification methodology. That means you can apply this methodology for any type of verification in the universe. Okay, so it is the industry standard methodology used for verifying complex digital chips. Okay, so not only for the simple things, but for also complex things, you can apply this UVM because of the availability of the default things. You don't need to anything by default. I mean, you don't need to develop anything from the scratch. For everything, one default library class is there. You just have to analyze which class you want to take it for your. Okay, UVM is highly effective. It handles the complex verification environments and improves the verification quality and supports reusable verification. As I told you, for everything, default classes will be there. So you don't need to develop anything from the scratch. So you can reduce the long-term project effort. So if you take Verilog to complete the verification, it is going to take 6 months of time. The same thing you can achieve through system Verilog within 3 months. The same thing you can achieve through UVM in 1 month. That is the effectiveness of UVM system Verilog over Verilog. Okay, so if you take 6 months of time to complete the project by using Verilog, you can do that in 3 months of time by using system Verilog. And you can do that in 1 month of time by using UVM. That is the advantage. Okay. And that is why every company, Intel, Nvidia, AMD, Qualcomm, almost every company is using this UVM. Okay, so this is the mandatory knowledge for a verification engineer. That means if you want to get a job in design verification domain, you need to have some knowledge on it. Okay, so this is how UVM test bench looks like. Okay, so we will discuss all these things in our regular sessions. So after UVM, also in order to get some experience, we will make you to do some projects on synchronous FIFO, asynchronous FIFO, and SRAM. Okay, so thereby you will get some hands-on experience how you can make use of the concept that you have learned in theory sessions. And you are going to use these tools in industry: Synopsys tool, Quastarsim tool, Cadence, Verdi, and Jasper. So all the tools will give the almost similar output, but depending on your requirement. For example, if you want to get the high performance simulation, then you can go with Synopsys. Okay, so if you are mainly focused on assertions and coverage, you can go with Quastarsim. Or if you want to get some parallel simulation support for the low verification support, you can go with Cadence too. If you are mainly focused on debugging, you can go with Verdi. So all the tools will give the same type of output, but depending on your requirement, on which aspect you are focusing more, depending on that, you have to select the tool. Okay, so these are the standards tools: Synopsys, Quastarsim, Cadence, Verdi, and Jasper. Okay, so after that, we will make you to do some industry standard projects. So wherever you go, you find APB and AXI interfaces over there. So in order to understand that, you have to go through some projects. And depending on the market situations, we will teach you one of the high-speed protocol. Okay, so why we call it as a high-speed protocol means the data communication is in terms of Gbps. Okay, so depending on the market situation, we will teach you one high-speed protocol. So as I told you earlier, try to learn the protocols as many as possible. Okay, so Python, as I told you earlier, so it is going to save the time because it is going to reduce the manual effort and improves the productivity. Okay, so it automates the repetitive tasks. So this type of scripting languages are very, very useful to automate the things. Okay, so what are the skills needed for the DV engineer role is you need to be familiar with the concept of digital electronics. In order to understand the RTL, you have to know the Verilog concepts. And the OOPS concepts, we are using it in system Verilog as well as in UVM also. And the debugging skills are very, very important because you have to find out the issue and you have to resolve the issue. In order to do this thing, debugging skill is very, very important. So if simulator is throwing any error, you have to find out from where the error is coming up and what steps you need to follow in order to resolve the error. And protocol knowledge, I have been telling you about this. And Linux and scripting language. So industry prefers Linux, and in order to reduce the time, you go with scripting language. And text editor, we are going to write everything in a text. So in order to make some changes or in order to edit those files, we need to be aware of commands and automation tools and languages, right? So these are the skills needed for the design verification role. Okay, so if you ask me what are the career opportunities you're going to have in design verification role is, at starting, you will be taken as a trainee engineer. After that, you can move to the DV engineer role. After DV engineer, after senior engineer and lead engineer, and the final I mean, the topmost hierarchical level is verification architect. So the training engineer means, I mean, any internship, if you apply in any company, they will take you as an intern. Okay, so intern means they will give you some small tasks to assess you. That means what type of effort you are putting in order to complete the tasks and what is your knowledge on the basics. So these things they are going to check. Okay, so it will be take from 3 to 6 months. In some companies, it might take 1 year as well. So during that time, they will check you what are your basics on system Verilog and how you are developing the basic test benches and how you are making use of the simulation tools. So they will give you training on all these things. Okay, so once you get an experience of 1 year, if they convert that into a full-time employee, you will be joined as a junior design verification engineer. So here you will be given some specification to understand it, and you will be asked to writing and running some test cases, and you have to debug some RTL issues, not major issues, minor issues they will give. So once you get 3 to 5 years experience, they will move you to the design verification engineer role. Okay, so during this time, what you need to do means you have to plan the test. That means how many test cases you need to develop. What should your approach for the verification, and have you covered all the things or not? And debugging complex bugs. So for the junior design verification role, they will give you some simple issues, but when it comes to DV engineer role, they will give you some complex bugs to resolve. Once you get 5 years experience, you have to develop the environments. You have to review the test plans and leading debugging efforts. Leading debugging efforts means if some junior engineer is suffering with some failure issues, you have to help him to debug those things. Okay, and you have to improve the verification efficiency. And after that, you will be given as a lead engineer. So what you have to do, you have to verification architecture planning. That means for the entire verification, how many agents you have to use, or how the environment should look like, what are the test benches you need to follow. Okay, so technical mentoring, that means for your juniors, you have to give your support. And when you integrate multiple IPs, how you need to resolve the integrational issues and complex level testing, you have to do it. And once you get 15 years of experience, it is a high level role. So you are going to define the verification strategy. So you are not going to develop anything, but you will give some guidance to the engineers. That means how should be the verification strategy, and you have to decide everything, whether you have to go with the UVM or whether your team has to go with the system Verilog. So everything you are going to decide it. Okay, so what is his name? I forgot. Harshit, right? So Harshit, as you asked me at the starting of the session, so this verification architect is going to decide whether any reusable frameworks are there or not. I mean, based on the requirement. For example, as we discussed about the 4G and 5G technology, right? So if already available things are there, so he doesn't go with the new ones. Okay, so he will do some modifications and he will make everything ready. But if it needs any extra other source, then he will hire it for something. I mean, he will hire that one and he will get that resource from the outside. So he is going to decide everything, whether the already available things can be reusable or does he need to develop anything from the scratch. So he is going to decide everything. Okay, so he is going to plan the reusable frameworks. Right?
Okay, sir. Sir, one more thing. Sir, in industry, you are an verification engineer, right, sir? You are using system Verilog test bench architecture or UVM test bench architecture, sir?
Most of the time we go with UVM, but if it is not needed to, I mean, UVM is a quite a bit difficult for a fresher. Okay, and it has lot of structure, lot of test bench structure. Even for a small thing also, you need to develop some 10 to 12 components are there. But for those things, for the simple things, you don't need to go with UVM always. For complex things, it is necessary, but for simple things, you can go with system Verilog. Okay.
Okay, sir.
The simple things, you can go with system Verilog. But as we deal with the system level verification and subsystem level verification, UVM, most of the times we go with UVM.
Okay, sir. Sir, one more thing. For the design, we are using Verilog as well as system Verilog, na, sir?
I mean, most of the time we go with Verilog and VHDL. In system Verilog, 85% of the language is meant for verification. 15% of the language is meant for design.
Okay, sir.
Okay, so you can remember in this way, for RTL design, we go with Verilog. For verification, we go with system Verilog. It doesn't mean that Verilog cannot be used for verification, and it doesn't mean that system Verilog cannot be useful for design. Both the things can be done. But most of the times, what we are going through, that matters.
Okay, sir.
Okay.
Yes, sir. Sir, one more thing. I'm facing difficulty while learning assertions and functional coverage. Can you suggest some resources to learn, and as well as how to learn UVM? Since I'm starting my internship from next month, can you suggest some resources so that it will be helpful for me to learn?
See, Harshit, assertions, yes, I agree to you that it will be very difficult for a fresher. But
yes, sir.
Once you get an experience of 4 years or 5 years, then you can write the assertions in an effective manner. But you have to get some experience for writing the assertion. That is why the team leaders won't give the assertions part to the juniors or interns. They will give the assertions to the employees who have more than 5 years or 6 years experience. For a fresher, it is difficult. I agree to that. And when it comes to UV, but as of now, you have to go through the basic parts of the assessment. That means what are the system functions we are going to use for the assertions, and how you have to observe the seniors, how they are writing the assertions. So through your observations and experience only, you are going to learn that.
Okay, sir.
But when it comes to UVM, I also agree with you in this aspect as well. So in order to understand the UVM, we need some time.
Yes,
I know
sir.
that. Okay. So for a fresher, fresher may find difficult to understand the UVM concepts. But once he gets the experience on UVM, he doesn't leave the UVM because of its reusability, its flexibility. Okay. But why freshers find difficult to learn UVM means, see, Verilog language is similar to C language. So as we already learned the C language in BTech, we can easily understand the Verilog language, right? And if you understand the Verilog language, most of the things are there in system Verilog. So as you already gone through Verilog, you can understand the system Verilog. And the system Verilog language concepts are there in OOPS concepts of Java and C++. And these are some general uses technical terms are going to be used over there. Okay, you can understand it. But when it comes to UVM, there will be new terminology. There will be new repositories. Okay, and there are some plenty of library classes. So you will get confused which class to use and which class to not use. And as the terminology that we are hearing in UVM for the first time, you may find it difficult. See, when you learn the C language for the first time, did you feel difficulty or not?
Yes, sir, difficulty.
But once you get habituated that, you got very comfortable with that one, right?
Yes, sir.
In the same way, UVM also, for 1 year or 1.5 years, you may find it difficult. Even I too face the same situation. Let me be honest with you. So when I learned the UVM for the first time, for 2 years, for the first 2 years, I too suffered a lot. But now, as I have gained some experience, I find it very comfortable with the UVM. So if you give me some design and if you ask me to verify it, I won't go with Verilog and system Verilog. I will directly go with UVM. That comfortability you are going to get it. Okay, that steeping curve might be very less, but trust me, once you get familiar with the UVM, you won't leave it. Okay.
Okay, sir.
So as the terminology is new for us, we may find it difficulty, but you please practicing a lot. Okay. And you please
Okay,
practice it thoroughly. You will find it very, very easier compared to System Verilog and Verilog.
Okay, sir.
Excuse
So
me,
what
sir.
about
Can you
functional coverage?
please-
Anyone, please?
Sir, can you please explain some different job roles?
Sorry, come again.
Sir, different job roles, sir, like RTL design for engineer,
Uh-huh.
like different. Give some information about that, sir.
I mean, what type of information do you need, Vinay? I mean, what are the domains roles are available in VLSI? Is that what you are asking?
Yes, sir.
As I told you earlier, so these are the domains available. Okay, so see, the first role is architectural, but you are not going to get this role as soon as you entered into the industry, because you need some experience to design the project flow. So as a fresher, you can enter into the design engineer role or verification engineer role. Okay, so in the front end. So I also mentioned those things in PPT.
Sir, one more question.
Uh,
Sir, what is the impact of AI for verification engineering?
so everywhere I'm getting the same question. See, an engineer cannot be replaced by artificial intelligence, but a coding person can be replaced by artificial intelligence. I hope you know the difference between a coding person and an engineer.
Yes, sir.
Right? So coding can be done by artificial intelligence, but engineering cannot be done by artificial intelligence. So it can be a software, or it can be a VLSI, or it can be any field. Okay. So a person intelligence cannot be matched with artificial intelligence. Okay. So verification engineer, what he's supposed to do, he has to analyze the things. So the test bench can be developed by artificial tools. The inputs can be developed by artificial tools. So everything can be developed by artificial tools. But the analyzation, debugging cannot be done by artificial intelligence. Okay. So if you know how to do all these things, so you cannot be replaced by AI. Okay.
Okay, sir.
Vinay, can you see my screen? Vinay, is he there? Vinay BL. See, front end roles are RTL design roles. So if you are good at Verilog coding, then you can go with RTL. Okay. And if you are good at System Verilog and UVM, that means OOPS concept and UVM concepts, then you can enter into verification role, design verification role. So formal verification is another domain, but as a fresher, you cannot enter into this formal verification. Sorry, it's my mistake. So for the fresher roles, formal verification, you don't have any chances. Once you get an experience of 3 years, then you can move to the formal verification. And DFT, design for testability. Okay, so I mean, once you choose the domain, the institute will give the enough training to get the job in all these domains. So based on your interest, first you need to choose the domain. So once you choose the domain and take the proper training from the institute, and you can apply the roles for these domains. So when it comes to backend, for planning, placement, and clock tree synthesis, routing, and static analysis team, and GLS team also there. Okay, that I am going to mention it here, not here, here. Gate level synthesis. Okay, but for a fresher, okay, so for a fresher, Design role is available. Verification role is available. PD role is available, not physical verification, physical design. For PD role is available, and placement and routing roles, these roles are available. So you can join in any one of these roles. Okay, so functional verification, design role, GLS team, PD role, placement and routing role, validation. Yeah, validation role is also available. Pre-silicon and post-silicon. Fresher can enter into all these domains. Okay, Vinay? Did I answer your question?
Sir, yes, sir.
Yeah, okay. So guys, you don't need to worry about the job because everywhere opportunities are there. And I hope you aware how this VLSI is controlling the market situation. So every service-based company, every software company is switching into VLSI. So you don't need to worry much about that job opportunity. You have to focus on how to get the skills. So if you have enough skills to get a job, you can get the job not only in India, even abroad also there are plenty of opportunities. So you can get job anywhere. You have to focus on to get the skills. Okay, don't worry about the job. Okay, so in all these companies, you have the opportunities, and there are many service-based companies which are offering the roles for the students. Okay, so you don't need to worry about the job. You just need to focus on the skills that you need to acquire in order to get the job. So these are the some product-based companies: Intel, AMD, Samsung, Synopsys, Qualcomm, Nvidia, Cadence, Broadcom. So I hope you're aware of all these companies. So you can get anywhere. You can get the job in any company, but you have to be strong in all the skills. So as I have mentioned, if you get proper skills in design verification, so you can get anything. Yeah.
Can we get that PPT, sir?
PPT.
Yes, sir.
I will share this to the management, and management will share this to you. Okay, I will give this information to the management that students are asking for the PPT, so they will share it.
Okay, sir.
Any other questions?
Sir, will the practice tools work on the MacBook?
Yeah. So these tools are work in any platform. They're going to work. And other questions?
Sir, as I said before, I'm starting my internship from next month as a verification engineer.
Okay.
What are all the things that I need to focus
You need
during
to focus.
this 1 year? 1 year. My internship duration is for 1 year, sir.
Okay. So where are you going to pursue this internship?
In Cadence, sir. Cadence.
Cadence, right? So you have to focus on, so as I in the PPT, as I have mentioned, you have to focus on system Verilog concepts and UVM concepts. So system Verilog concepts, UVM concepts. So as you are entering as a intern, right? So
Yes,
you
sir.
have to focus on how to make use of the tool for the, I mean, to analyze the waveforms, to see the coverages. So these are the things you have to focus on.
Okay.
How to develop the test bench for smaller projects.
Okay.
Basic test benches. And if it is possible, also try to learn the things how to develop the test cases.
Okay, sir.
So these are the areas you have to focus on. And
Okay.
if any possibility is there, try to learn the protocols as well.
Okay, sir.
Got it, Harshit?
Yes, sir. Got it.
Yeah.
Hello, students. Sir, this is for students. Can you get your all mail IDs for communication about the VLSI? Hello. Hello, can I get your mail IDs? Arshit, Varshim, Chetan.
Okay, guys, you please carry on. I'm going to end the session now.
Thank you, sir.
Okay. Thank you, sir.
Yeah. Thank you, guys. Thank you for joining the demo session.
Thank you, sir.
Thank you, sir.